Good morning everyone. Thank you for coming back to our workshop on Sunday morning. I hope you had a very enjoyable conference so far. So we will continue for this exciting workshop. So now again, this workshop is about excess water challenges. So yesterday we have talked about something from the sky. So what happened for the future climate change? And we also have some engineers from Hong Kong talking about the recent solutions about landslides and also flooding. So the workshop today will be more focusing on the engineering technologies solving a problem about landslide or slope stability. Okay, so we have a number of overseas speakers from the UK and also the North America to share their experiences on the recent researches of the technologies they developed. Okay, so this is a timetable. So we will have a break around 10:15. So the first speaker will be Stephanie. So I will do a quick introduction for her. But let me find your presentation slide. Yes. Right. Okay. So is that good? Yes, that's yours. Right, so Professor Stephanie Finite is Professor of Civil Engineering and also Dean of the Strategic Projects in Newcastle University in the UK. So she has led and also leading multiple research projects on infrastructure embankments and also the impacts of climate change. So Stephanie has pioneered a very interesting concept, which is called the urban laboratory. So this is an initiative aimed at developing and using full-scale operational infrastructure as a laboratory in which to develop research and impact. Okay, so she's also the founding director of the spin-out company Electrokinetic Limited, specializing in infrastructure remediation. Okay. She also awarded a Royal Academy of Engineering Fellowship with Europe for embedding sustainability and design throughout the civil engineering program in Newcastle University. Okay, so without further ado, I invite
Good morning everyone, and thank you for giving up your Sunday morning to be here. Much appreciated. So before I start, I must acknowledge that the work that I'm going to present is been developing over quite a number of years and in partnership with all of these other universities. So I lead it, but without all of these other contributions, then I would not be able to present the work to you today. So we need to sort of think it's very much a combined effort. So just a little bit of context. I'm going to be talking about long linear infrastructure. Primarily that's road and rail cuttings and embankments. And I think to cut it down, to keep it to one infrastructure for this morning's presentation, I'm going to concentrate on the UK rail system. And the context is that our climate is clearly not as extreme and does not have the extreme events that you experience here. However, our climate is still changing, and our weather does produce failures on the transport network, and the impact primarily is on disruption. So because our transport infrastructure is one of the most heavily used in the world, it creates all of this disruption. For example, the UK rail network takes 50% more daily traffic than the French network, and France is between 2 and 3 times the land area of the UK. So that gives you an indication of how intensively used it is. And couple that with the fact that our rail network, much of it is over 100 years old, much of it is over 150 years old. So it's an aged infrastructure. And in 2015, which was a wet year, there were over 2 slope failures on the rail network a week. So they're not huge failures, but the map shows you that a very small failure here around Birmingham, which is our second largest city, creates all of this disruption over the entire, the whole of England, well, up into Scotland. So it creates all that disruption with one very small problem. So that's why, and Network Rail already spend 117 million pounds sterling on maintenance every year, which actually isn't enough. So we need to work out in that changing climate how we better manage the network to minimise disruption, to minimise economic impact, and the impact that it has on people's daily lives. It isn't just rail assets. There are, you know, the road asset and the embankment dams, etc., all applicable, but I'm going to concentrate on rail today. So this complicated diagram is the current approach that Network Rail have to managing their asset. And I'm not going to talk all of that through. It seems I've taken it directly from their Earthworks asset management handbook. And the thing to concentrate on is this bit about prioritisation. So we need to prioritise where we need to invest. And part of their asset management is about forecasting where is going to deteriorate. So the research that we've been doing in partnership with Network Rail has been concentrating on better forecasting where the failures may occur and helping them to then feed that into their prioritisation plan of where they need to invest. Just to, again, just put some context around this. This was an extremely wet, for the UK that is, extremely wet summer. And that actually will come back to the fact that this was summer wetting, not winter wetting, which is what we normally have. And these are the types of disruptions that occur. This was a representative from Network Rail who own and manage the rail network, stood in King's Cross Station, which is the station in London that deals with all the trains that are going north, south to Scotland, so between England and Scotland. And that's where I would get a train if I was in London going back to Newcastle. And he's trying to explain why a failure has caused all this huge disruption with all these people milling around in King's Cross Station. We don't have many fatalities because of slope failures, although the risk of that is still there. So if a cutting fails and puts material down onto the line, such as this, if there was a rail line here, then a derailment has the potential then to cause a fatality, and there have been a few. Okay, so what I'm going to talk about today is mostly about clay materials. So they're quite different from many of the materials that you have here, but the reason why we have concentrated on clay materials is this is a map of just the shrink swell materials, those materials that shrink and swell with changing water content. There's the map of the rail network and the map of the road network. And I guess because of where the networks are intensively used, primarily around London, we are very London-centric, but London across to the west and London north, those are they are quite a significant material for the transport network. And again, the way in which Network Rail have started to think about which slopes are significant in terms of that deterioration is that they've had one of their consultants, Mott MacDonald, map out all of the different geometries of the network, the slope angle and the slope height, and look at where the failures have occurred. So these red dots are the failures, but they've only just started doing that, and they have a maximum of 10 years of historical data that they fed into that. And of course that isn't looking forward at the effects of increased traffic on the network. Actually, we can only maintain our networks in the middle of the night, and actually the public are pushing for 24-hour service, and of course it doesn't account for the effects of a changing climate. And in the UK, broadly speaking, that changing climate is warmer summers and generally wetter winters, but with that wetter being more extreme events rather than long drawn-out wetting. And that's primarily for the southeast, and there are variations on that over the country, but we'll talk about that later. So we are trying to work with the way that Network Rail are working to try and advise them on what could happen in the future in a changing climate. And the indications that there may be more failures because of this changing climate are there already. This is a plot of soil moisture deficit, which is effectively how much capacity the soil has to take in water. It's sort of water holding capacity. And when the soil moisture deficit is 0, it means it's full, essentially. And so at the points where on the rail network where the soil moisture deficit goes to 0, sorry, can't deal with two screens, where the soil moisture deficit has been 0, then there are failures. So it looks like broadly speaking, wetter periods cause these failures. So we have reason to be concerned. So the research that we've been doing is conceived within this sort of diagram. So what it's a plot of is performance, and we can talk about what performance is later, against time or age of the asset. And what it says is that a new asset takes time to bed in, and so doesn't reach its full performance quite immediately. It then performs reasonably well over a period of time, and then it starts to, it's the deterioration that is occurring, means that at some point, when it gets older, it starts to not perform and becomes unreliable. And the question is, what do those deterioration curves look like? How is it deteriorating with the effects of climate and weather? How fast is it happening? And when should we intervene to do something about it? So when should we do it from a technical point of view, but when should we also do it from an economic point of view? When is it best business to intervene? And what sort of intervention should we make? So this is a UK context. We've got HS2, which is our high-speed line that hasn't been constructed yet. So it sits down here. And our older assets, Network Rail assets, which are 100, 150 years old, are sat there and not performing that wonderfully. So the research programme is RC1, that's Research Challenge 1, is looking at material degradation, the actual clay. Research Challenge 2 is looking at the scale of the slope, the asset, and how that is performing. And RC3 is around looking at the network and the economics of all of this. And I'll just say a few words about each of those, not many. Right, so I'm not going to do the words. What we've proposed and what we have some evidence for is that the clay material itself that makes up these assets deteriorates or reduces performance because of wetting and drying. So hopefully this will be a pointer. No, maybe not. I don't press. Does that work? Oh yeah. So with wetting and drying, this is the clay under the microscope. It begins to crack and break up. And what that does is it causes the material to change its behaviour it can, for the same water content, it can no longer hold on to the same amount of suction. Same water content, reduced suction. And that reduced suction then changes the way the water flows in and out of the soil. It also reduces its strength. So just because it's lost its suction, it loses its strength, which is this, it loses its strength. And that small amount of loss of strength then could trigger some movement, which then we are hypothesizing leads to then progressive reduction in strength, progressive failure, and ultimately the failure of the slope. And that's our hypothesis. We have some evidence and we're looking further into it. In terms of asset performance then, we've been looking at gathering field data from the asset owners, but also our own field data. And we've recognised it's important to have a long data set because you need to be able to have a data set that has those extremes in it. If you don't have the extremes, then you can't really make any sort of judgment about what might happen in a changing climate, and that's really important. And in order to look to the future, you need some sort of tool, and we've chosen to use a numerical tool that allows us to look further into the future. I'll just say briefly a few words about each of those, not much. So we've got an instrumented highways cutting down, this is near London, it's in London Clay, and back in 2005 we constructed a test embankment. And so we've got a cutting, we've got an embankment, and these are the assets, the research assets that are giving us these long-term data sets and also allow us to experiment imposing different climates on that embankment, different water regimes on that embankment to study the effect. And I won't say any more now, but if anyone's interested, I can say that. The modelling approach, without going into the detail, we've coupled a hydrological model that we can impose the climate and the climate change boundary to, with FLAC, the geotechnical model that allows us to look at deformations and allows us to write our research code to it so that we can embed the learning we've got about the materials into the code. We've learned a lot about input parameters, which I won't go into now, but I could tell you about later. And the key thing here is with the weather, we've taken the UK Climate Impacts Programme data, which has downscaled the global climate change scenarios to a 2.5 kilometre grid, I think I'm right. And you can go on a website and click on any location in the UK and get the future climate scenarios for that. And we've developed a technique for taking that and putting it and inputting it into the model, which I won't go into, but I could talk about. And what we've produced then, some of the results we've produced, is this long-term deterioration. So this is our performance versus time for current and the future. And what you have here is performance. In the top we've got our pool water pressures with different depths. So this is the most shallow one, that's why it's moving quite as much. And with the weather data, what we've done actually is purposely, in the first instance, taken out the extreme events. So it might sound odd, because we've taken out those things, but it's because what we wanted to do was look at the long-term deterioration. And if you've got a model that's running for 150 years, simulating 150 years, you don't want it failing at year 2, because you've got this spurious extreme event occurring. So we took those out. We've then got the background long-term deterioration, and then we've put the extremes back in so that we can look, and we need to do more of that because we don't actually know what an extreme means at the moment. So from that pore water pressure data then we've produced this performance curve, which we've chosen factor of safety. We could choose something else, but we've chosen factor of safety, and you can see that reducing factor of safety with time and then projected into the future. And what we've found is that if we take that out, I mean, this curve could actually move downwards because the models are perfect here. So this is a representation. Is that, you know, for our modern highway slopes, they're looking potentially, they deteriorated somewhat, but our rail slopes are those that have deteriorated the most, and it's because they've deteriorated that then they're more vulnerable to the extreme events, which is one factor that explains why you can have the same slope with the same geometry in the same material, and one will fail with the same weather event and one won't. It's not the only factor, but one of the factors might be because of this, the long-term deterioration. And because there's a whole load of other work about validating the model, which I won't go into, but we then started to look at what can you do to increase the performance of your slope. And so these are those deterioration curves. We've looked then at, for this particular scenario of slope, it fails after 40 years. But if you put a tow drain from the start, you design your slope and you construct it with a tow drain, it fails after 100 years. So the message is you put a tow drain in your slope and you get 60 years of extra life out of it, which is quite a message to give to the asset owners. And it's one that they start then to actually recognise, oh, that means something to me. So more work to do on here, but it's a start. And then thinking back to those assets then, and the way in which the asset owners and the consultants have started to work. We've done a little bit of work, so this is absolutely, I've produced this especially for this presentation, so don't ask too many questions about it. So we've taken this part of the graph, and we've taken slopes with those particular geometries, and we've run the model and we've looked at the deterioration of those, and we've looked at how many years to failure. So right down here we've got 180 years, which actually, when you consider some of these assets are 150 years old and the models aren't perfect and none of the parameters are actually correct, actually, you know, that is close to failure potentially. And those that are the taller ones, the higher, steeper ones, they've already failed, which kind of bears out some of that data that we've already got about the asset. So we're pitching about in the right sort of place, I think. And these are the deterioration curves for all of those slopes. And we could talk in more detail, but I'm conscious of the time. So what about adaptation options? We've produced a deterioration curve, and I won't just ignore the time really, and we've looked at intervening before just as the asset starts to deteriorate, when it's deteriorated by 50%, and when it's failed, and looked at putting adaptation options in at each of those times. And what we've got then is just for a drain, putting a drain in. If you intervene early, you get 100% increase in serviceable life. If you intervene mid-deterioration, you get 57% extra life, but if you wait until it fails, you don't get anything. Now all that might not be absolutely right, but it sends a message that actually what we need to do is adapt now. Don't leave it until the asset has failed. I'll skip that one. So, conclusions. We shouldn't just be thinking about extreme events. Actually, things are constantly deteriorating, and that makes them more vulnerable. Couple that with the increased utilisation and the developments around all our infrastructure, actually that increases both the likelihood of failure and the consequences, so we're increasing the risk. We need to look to the future, and the future is different from the past. Everything is changing, including all those soil parameters. And so we need to have both a sound underpinning science coupled with a compelling business case in order to make the change. You need both. And the science needs an understanding of the climate, the soil, and their interactions, and vegetation's in there somewhere too, which I haven't spoken about, and also the data. We need good data. And in order to with all of this, to make a change, you need to engage simultaneously with both the engineers and the policymakers, and with messages that they both understand.
Thank you, Stephanie, for a very interesting talk. So we'll leave the Q&A after two more presentations, then we can have a Q&A for all three speakers. Okay, so for the second speaker we have today is Professor Johan Griffiths. So he is a professor of civil engineering at Colorado School of Mines, and he is also a former director of ASCE, the American Society of Civil Engineers. So his research interest lies in the application of finite element and also risk assessment methodologies in civil engineering. So he is also co-author of 3 textbooks. So the first one is the programming, the finite element method. The second one is the risk assessment in geotechnical engineering, and the third one is numerical methods for engineers. So I can see many of us here are postgraduate research students. So if you're working on numerical modeling, finite element, those are 3 excellent textbooks. And he has also translated in the Chinese versions of some of these books, so that would benefit to some of you maybe. Okay. So without further ado, may I invite...
Is there a way of temporarily just going to the PC only, disabling the screen? Or
This.
if I just fire it up and show all the slides down the side, and then it's this one. Don't worry, it's not essential. Let's just go.
I froze the screen.
Good.
So if
Okay, now we can.
If you don't unfroze it.
Open it up again. Thank you.
Yeah.
Unfreeze.
If you don't unfreeze it,
Ah, that's neat.
and that one as well.
Thank you, Anthony. Thanks for coming. Sunday morning. Boy, it's funny how somehow it comes full circle. When I started at Manchester University, any number of years ago, P.W. Rowe, some of you may have heard, hired me, and one of his obsessions was drainage, drainage, drainage. And when it comes to instability in geotechnical systems with where pore pressures are your problem, then it's obvious that we want to get rid of those high pore pressures. This is very much like a soil mechanics class, I'm afraid. A little bit of a break, perhaps you can relax. A few pictures, of course. Well-known landslide in California on the left, triggered by rainfall, and a sort of finite element-y picture of a tailings dam that some mining facility which failed during a wet event that increased the water level on the upstream side. You know, just a slight distraction here. When I was waiting for my boss yesterday, I was thinking how inspiring and uplifting, you know, and elegant this mascot of the Hong Kong University of Science and Technology is. And I had some doubt as to whether the Colorado School of Mines had quite got it right, but didn't quite carry the same, you know, message.
The head up,
And most American universities have sort of lions
We have
and
a
tigers
lion.
and buffalo and things like that. All right, so a little bit of basics for everybody that you all know already. Soil strength is a function of effective stress, and especially frictional soils. And I missed that one. And if we get to the simplest and best known failure criterion is Coulomb, which states that strength is a function of effective confining pressure, friction, and cohesion. And where does the frictional strength come from? It comes from effective stress. That is given by our famous Tsagi's effective stress equation. So it's obvious, just looking at this equation, that high water pressures are usually going to be detrimental to the engineering properties of soil. If you increase U, this is generally going to go down. If that goes down, this goes down, that goes down, and things get less safe. But perhaps it's better always to focus on more fundamental things, that the actual effective stress is the thing that is fundamental. U would certainly obviously influences the effective stress. But I suppose one of the themes of this chat is that we should focus on sigma prime, probably ahead of U. Where sigma prime is the difference between the total stress and the pore pressure. Climate change means many different things. Of course, this particular session we're interested in the wetter side of climate change, but on the other end we have drought and drying of soils, which causes shrinkage and other kinds of damage. This is from China somewhere, with dozens of landslides. Fortunately, most of them are in the middle of nowhere, so they have low consequences. We talked a little bit about risk yesterday as being probability of failure weighted by consequences of failure. Of course, if one of these happens in Hong Kong, in the island, then the consequences are enormous. Here's a list of, just off the top of my head really, when I was preparing these slides, of things where water pressures obviously can cause problems. Liquefaction, landslides, erosion, slope stability in general, like we heard just now from Professor Grendin, swelling soils, an issue in many parts of the world, suctions and unsaturated soils, and I'll summarize it here. So I'm not going to go through everything, but just to show a few pictures. Probably the most famous liquefaction photo of all time, right? Niigata, 1964, where these apartment blocks just tilted over. I think they took a minute or two to actually reach that orientation, so people were able to come out the windows and walk down the front of the building. Far more people were actually killed the same year in Alaska, another earthquake, liquefaction. Here's a rather dramatic one from Turkey. Liquefaction, as I'm sure we know, is caused when loose-ish, saturated, granular soils are shaken up and they want to densify, but because the water's in the way, they can't densify immediately and the water pressures rise, effective stress falls, and you get liquefaction, at which point, of course, all the water pressures escape and you get the ejecta coming out of the ground. Absolutely related to high water pressures, and of course, climate change is going to cause, if you have heavy rain and inundations, then the water table is going to be higher, you're more likely to get liquefaction. Landslides have been a very large topic for this meeting, this last couple of days, for the geotechs at least, and natural slope instability due to intense rainfall or irrigation. There's some very dramatic cases of people, I suppose, innocently enough, watering their crops and causing remarkable instabilities. The Chinese landslide. This one was a notorious one in Washington State 4 or 5 years ago. 40 or more people were killed by this event in Washington State. Here is Washington State, in fact, and a map like this absolutely shows the correlation between high rainfall expectations and these little stars are locations of known landslides. We all know the two go hand in hand. Here's one in China, a landslide caused by irrigation. It's a kind of very dramatic graph of a factor of safety of a slope. In fact, it's rising slightly, maybe due to some drying phase, but then the irrigation started, and wow, what happened? The water inundated the ground. Perhaps there were suctions in there, they were eliminated. The effective stresses fell, and the strength fell, and so failed. Erosion is most documented, most damaging when it occurs with earth embankments and dams which are holding back water. Erosion is when soil particles are being moved by seeping water. Well, if dams are designed very well, they're designed with filters to stop this sort of thing happening, to stop the movement of particles. But of course, these are very complex systems. This is one of the most notorious erosion failures in the US back in '76, the Teton Dam. On its first filling, a small leak was noticed on the downstream side. Slightly muddy leak, and it's always more worrying if the water that's leaking is muddy because it means it's got particles in there. 5 hours later, this had happened. As quick as that. People were killed, but there was time to get some evacuation downstream. This is a picture from a Japanese event. This didn't collapse completely, but you can see very clearly the erosion channels. I have a PhD student right now looking at erosion modelling. It is the leading cause of failure for embankments. So rising water tables, high inundation events are going to make your erosion problems more likely to occur. And it's the responsible mechanism for most incidents involving dams and levees. These slides came from the Bureau of Reclamation and the Army Corps of Engineers. So erosion usually works its way upstream. It's kind of counterintuitive, right? But they always start at the exit points, and then if things don't go well, they propagate upstream. And so this is a great loose channel, a pipe, basically, of water and soil particles being moved. That one was in the embankment itself. This is one which it propagated in the foundation. It's called backward erosion piping. It's a very special type of erosion that works its way upstream. Of course, if it reaches this point, it's all open. The channel reaches the upstream boundaries. Slope stability, well, of course, is a vast subject, and we all know that water affects the factor of safety. The infinite slope is regularly used as a starting point for landslide modelling, in the sense that it's a long slope, generally translational mode of failure. We don't need to derive all the equations, but this is one of the very few slope stability problems that actually has a closed form equation. All slopes had a nice formula like this. You know, Bishop would never have been famous. But, so here's an equation for this particular slope where we have a parallel seepage line running down the hill. I've got this parameter d, which is the depth, vertical depth of the water. I suppose we could have different unit weights above and below, but frankly, if you make them the same, it's conservative, as far as I understand. Just go back one. How do you go back? Oh, this thing, sorry. I think. Any idea how you go? Oh, what did you do? Yeah, I mean, if we make the unit weight constant and let's assume it's pretty much saturated everywhere, then the equation simplifies quite a bit. So here's a plot just to show the influence of dW, on factor of safety for a typical set of properties here. Friction cohesion given here. If dW is small, then the factor of safety is low. dW increases, the water pressures get smaller, and the factor of safety goes up. So it's a very obvious relationship there. Water pressures are bad for stability, and in this particular case, of course, it might even fail because this example passes through the factor of safety equals 1 point. Finite element slope stability. I think I saw a finite element mesh just fleetingly in your previous presentation just now. I think finite element slope stability is gaining wide acceptance as actually a more powerful alternative to limit equilibrium, with strength reduction methods to estimate the factor of safety. And of course it's been validated many times against classical solutions. Here's a strength reduction factor. So we're gradually weakening, we apply gravity, we gradually weaken the soil by dividing by a strength reduction factor. At some point, if you weaken the slope enough, it fails. It's bound to. And that's usually accompanied by a large increase in deformations. And when that happens, the strength reduction factor is the factor of safety of the slope. It's the same definition as Bishop or anybody else has used. It just seems back to front, but it's exactly the same. It's a measure of, basically it's a measure of how much stronger the soil is than it needs to be to support gravity. So what about water then? Oh, just one other thing about the finite element method, which I showed this slide. One of the benefits of the method for slope stability analysis is that when you've applied the strength reduction factor, in this case this is a Canadian project that I don't think ever quite got built, but it became a very popular benchmark problem. Something to do with damming off the Hudson Bay and turning it into a hydroelectric system, but very layered soil, obviously, with several different strata. With strength reduction, this thing failed when the strength reduction factor became 1.27, and the finite element analysis gave us this failure mechanism. Naturally, it comes out of the analysis. I didn't have to tell it to search for a circle here or a translation there. This is probably the biggest advantage of the method, I think. The failure mechanism comes out of the analysis as an integral part of the analysis. So it'll give you the factor of safety and the critical failure mechanism. The mechanism seeks out the path of least resistance, essentially, the place where the strength is unable to resist the shear stresses caused by gravity. For water, we have to make some small modifications to include water in these finite element analyses. What we do normally is what I think everybody else does, is we assume that water pressure at any given point is equal to the vertical weight of water above that point. So the water pressure U at A is just HA gamma W. That's slightly conservative, actually, because if we went to the trouble of drawing a flow net on here, which is a pain in the neck, but if we did, we'd find that there was an equal potential passing through A that intersected the free surface at 90 degrees, slightly lower than the place where we started. So I think we're okay. This assumption, a somewhat conservative assumption, is also a simple assumption, which is a very good combination. Simple and conservative, can't argue with that. Out here, in the sort of open lake or reservoir, what we're going to do here is just throw away the reservoir and replace it with equivalent nodal forces, hydrostatic pressure on this outer boundary. So obviously along this stretch, the water pressures are rising linearly, and then along this horizontal line, it's a constant pressure. So the program will automatically generate the basically nodal forces on the surface of the embankment. This program is freely available on my website if you want, and you can run it, source code. But I wanted to show you a couple of sort of slightly odd examples where perhaps our intuition is not quite always right at first thinking. Here's an example where the pore pressure goes down and the factor of safety goes down. That's not what normally happens, right? We usually expect water pressures to rise and the factor of safety to fall. So this happens in a couple of cases I can just show you. This is a rapid drawdown problem, which we all learned at university that it can be a problem if there's a sudden drawdown of a reservoir, and we assume there's little time or no time for drainage, then we have a dangerous situation, because here's a case where I have initially actually an underwater slope, and I've drawn down this water to half the height of the slope. So all of a sudden, this water level here has come down to here. And the most pessimistic assumption we can make is that there's been absolutely no time for drainage in the soil. So this is all now heavy, wet stuff that was originally buoyant. And we've also lost the supporting hydrostatic pressure that used to be here as well. So if we run this through a finite element program, I don't suppose it has to be finite elements, we'll find that factor of safety comes to 1. So this is an example where obviously the water pressure has gone down. But what happened is that the total stress also came down by more. I suppose you have to think a few minutes about that. But water pressure clearly falls, no question about that. But the total stress has gone down by more. So if you think of Terzaghi, then sigma prime has gone down. So sigma prime is more fundamental than U, as we know. Here's another curiosity. This is perhaps more of an academic exercise, but another example which is rather intriguing. And in fact, we're looking at it again now. It's been around for quite a long time, this phenomenon. What I call slow drawdown. So this is where the water level through a slope is brought down slowly enough that the water remains horizontal at all times. If we now plot the factor of safety of this slope as a function of d, so d can start off here, up here somewhere, and then gradually we bring it down slowly enough that it's always horizontal, we get this rather remarkable result in some ways. Here I've plotted dw non-dimensionalized by dividing by h, just to keep it simple. Down the left on the y-axis we've got the factor of safety. And we get this thing that has become called the critical pool level. We get a certain level of the horizontal water table where the factor of safety is a minimum. Then it starts rising again, somewhere around 0.7, the height. 0.7 seems to be a kind of fairly standard minimum point. But I mean, we can think about this stretch of the graph. While we start increasing dW, obviously the pore pressures are falling, no doubt about it. But again, the total stresses are falling by more. It's a fairly subtle combination to explain this minimum, though. I haven't got time to do it now. But it's another example of U and sigma falling, but not by the same amount. Obviously the factor of safety is falling, sigma prime is falling. Then sigma prime starts to come up again. So it's a kind of more of a curiosity question to my mind. We did it using finite elements and limit equilibrium just to make sure it wasn't a crazy result. The critical pool. So in fact a fully submerged slope is safer than a dry slope. It's fully submerged. Of course, once the slope is underwater, it doesn't matter how deep the water is. It could be an inch deep, The water here could be 1,000 meters, or I shouldn't change units halfway through my sentence. Anyway, a submerged slope is a submerged slope. So this line, if I produced it further to the left, would just be a horizontal line. How are we doing? Good. I mentioned swelling soils, but it's a rather special problem in the western United States. I don't know, you probably have many cases in China too, but swelling soils are a particular type of clay, monzonite, bentonite type clays. If they get wet, they swell and cause quite significant damage. In fact, in Colorado, it's one of the largest insurance claims in the civil engineering business. There's claims for damage to people's houses due to swelling caused by water. And basically, it's desert, dry, arid land where people have started building houses and putting their subdivisions and started watering their lawns. Furthermore, in Colorado, we have these deeply tilted bedrock stratigraphy. But some of these are more swelling than others, so you get these curious sort of bands of concentrated swelling. And here's a nice little picture of. In fact, my first house, I had a big insurance claim, which is a little bit embarrassing. Suctions. I borrowed this slide from Atkinson's International Society seminars. But we all know a UU test on a normally consolidated soil, which has no cohesion, has strength. Why? Because of suctions. You take this out of the ground, the sample, and it's you unload the sample and you get suctions. It has some strength. But if you inundate the sample, if you stick it in a bucket of water, what happens? It loses all strength. So it's just a nice demonstration of suctions in a more traditional context. So, you know, unsaturated soils are a big topic, and I hardly need to tell some of the people in this room. Unsaturated soils have locked-in suctions. They cause an increase in effective stress and improved engineering properties. Some existing and natural slopes that have been around for 100 years or more maybe are stable because of suctions locked in there for many years. Inundation, wetting, drying causes cracks and starts to gradually remove the suctions. And of course the effective stresses come down if the suctions go away. In practice, designers are reluctant to rely on suctions though, because they don't trust them. But I think with some clever engineering and maybe some vegetation and so on, you can rely on them. Here's a very an old paper. I worked with our friend Dr. Ling Lu for a short while. I think he's coming to visit you next year. We did some finite element analysis of unsaturated soil, and we included, I know nobody can agree on this thing, but whatever model we were using generated suctions above the water table, which decayed in some way depending on the type of soil. And maybe I shall just show you this graph, which was one of our results. This is the steady infiltration or evaporation of a particular slope. Here's the factor of safety. And initially we had high infiltration and higher pore pressures, but sooner or later they start to fall due to the removal of suctions. Anyway, that's getting a little more technical. Let me just summarize. Oh my goodness, where did that come from, that G? Based on Tertaghi's principle of effective stress, water can have a profound impact on geotechnical stability. Stop. Several examples, we've got a slightly different version of PowerPoint or something, that's what's happening. Several examples have been presented, all of which involve geotechnical problems accompanied by a falling effective stress. Problems are usually related to a rising water pressure, but we also described a couple of rather interesting cases where the water pressures fall, or the total stresses fall by more, causing a similar lack of stability. I suppose that's a little picture of total stresses falling by a lot, U falling by less, but nevertheless, sigma prime falls too. All the programs I mentioned, and I didn't mention many, but on my website you'll find a pile of stuff. If you're interested, you can have a look. And thank you for your attention. Shishi.
Thank you. you, Professor Griffiths, which remind us a lot of very important concepts of soil mechanics and also slope stability calculation. Thank you very much. So our third speaker is Professor Li Zhang, who is Chair Professor in the Department of Civil and Environmental Engineering in this university. So he is also the Director of the Geotechnical Centrifuge Facility in this university. And he's also the Changjiang Scholars Chair Professor in China. And his research includes slopes and embankment dams, geotechnical risk assessment, reliability-based design, and power foundations, and also centrifuge modeling, of course. And he has led a project on landslide risk assessment and risk-based design for the reconstruction of a major highway near the epicenter of the Wenchun earthquake area. So I invite Mr. Zhang to give us his talk.
Thank you, Anthony, for your kind introduction. Ladies and gentlemen, my great pleasure to present to you some of our recent work at the university. So I'm just going into the topic right away. So today I will first talk about landslide risk in Hong Kong in extreme storms. Then try to introduce a proposed stress testing framework for managing landslide risk and steps for implementing this framework. And lastly, we'll try to illustrate the uses of this framework to Hong Kong Island, entire Hong Kong, and slightly future Guangdong, Hong Kong, Macau Bay Area. So a larger storm can cause multiple hazards. First of all, surface runoff, right, and then associated surface erosion, flooding. Also, some of water will infiltrate into the ground and cause slope failure. So soils from slope failure and erosion, so when mixed with excessive surface water, will generate debris flows. So we can have several hazards in the same event, and we can hardly separate them. For instance, during the storm in June 2008, which was mentioned by Julian and Raymond yesterday. So that storm hit Hong Kong, Lantau Island, and generated about 1,500 slope failures, 900 debris flows on Lantau Island alone, and a lot of flood spots across Hong Kong. Lantau to Hong Kong people is quite remote. Question is, what if the identical storm hit Hong Kong Island, which is heart of Hong Kong's economy? On Hong Kong Island, the natural terrain is quite steep, so 30% of natural terrain is steeper than 30 degrees. And if any slope failure, debris flow occurs, then the densely populated area will impact right away. Yeah, indeed, Hong Kong Island is traditionally a landslide susceptible location. Previously, a lot of landslides happened. For instance, the famous Portland Road landslide in 1972, which killed 71 people at that spot. So question still, so if the storm which hit Lantau Island, hit Hong Kong Island, what can happen? And also, if even larger storm hit Hong Kong Island, which can happen? So those are questions we need to answer for climate adaptation and preparedness. Previously, colleagues from GEO in Hong Kong have done excellent work. They did statistical extrapolation, for instance, establish, first of all, empirical rainfall landslide relationship, and then extrapolate using the relationship to extrapolate to future scenarios. For instance, if a similar storm which hit Lantau happened on Hong Kong Island, then a lot of landslide can happen. So some of them, a lot of them would hit people, affect the road. And even larger storm happened, something with the magnitude of Typhoon Marav in 2009, hit Hong Kong, then a lot more serious consequences can happen in Hong Kong. Of course, such kind of statistical extrapolation is relatively easy to apply, but of course, we still have some concern on the uncertainties associated, extrapolating to the future, which with rainfall events which haven't been experienced. Also, statistical analysis gives us trend, but not exact locations or size of landslides. And sometimes a natural hazard may be followed by some other either natural or technological hazard. For instance, during 10 years ago, during the winter earthquake, the Beijing town, first of all, was stricken by earthquake itself, and then by large landslide, and then by dam-breaching floods afterwards, and then later on, repeated debris flows, just one location, lot of hazards, which occur successively. So sometimes it's a chain reaction similar to that, which could cause the largest damage. So we need to consider that. So to answer some of the questions, so Hong Kong University, working together with University of Hong Kong, GEO, and HKO, worked on a project coping with landslide risk in Hong Kong under extreme storms. So some of colleagues were involved, Professor Charles Ng here, T.C. Lee from HKO, who presented yesterday. So the primary objective of this project is to develop a stress testing framework for assessing landslide risk in Hong Kong on extreme storms. Stress testing is not new. Actually, it's frequently used in the financial sector. When we talk about extreme event, certainly the number of incidents is relatively limited. We cannot establish nice probability distribution with such few number of cases. So stress testing is a good tool to handle such low probability, high consequent events. Stress testing is defined as target reassessment of safety margin of a target system in light of extreme events. For instance, let me just take a banking system example. Let me just first define the banking system and then assume some shock. For instance, the bankruptcy of the Lehman Brothers, so which will cause the business partners trouble. Then we try to assess the net loss of asset of the banking system, which will be the first round of so-called stress testing. Then after we look at the banks affected, some of them may fail. Then we need to look at all other banks which do business with those failed. Then we need to use a matrix to look at all those, so to assess the impact of all associated banks, and then go to the second round of assessment. Well, this process in a natural hazard case is actually same thing as something we call cascading hazards. So we propose a similar framework for evaluating a Hong Kong slope safety system. So in our case, stresses are not bankruptcy of banks, but in our case, particularly today, rainstorms, heavy rainstorms. So we need to define critical rainstorms, plausible rainstorms on the considering climatic change. Then we need to evaluate the impact of such load on the slope system, including sizes, locations of likely landslide or debris flows, and the impact or consequences caused by those hazards. Then we can consider some management strategies. For instance, through such impact analysis, we may find out the bottlenecks or weakness or weak spots of the system, and then propose some change or engineering measures to cope with such problems. So whatever we propose, we need to conduct a reassessment of the effectiveness of such systems. Sometimes some proposed measures may not really work well. In doing such assessment or in implementing such so-called stress testing framework, we do need to tackle a few technical issues. First issue is the ability to simulate the physical process of several hazards. landslide, or landslide erosion, debris flow, and the impact of those things on buildings, for instance. Secondly, we need tools to assess the risk or consequences of failure. And lastly, we need to integrate some social response preparedness aspect with technical aspect. So let me take Hong Kong Island as the first test set. So first step, we need to understand Hong Kong Island a little bit, including solid geology, superficial geology, topography, and eliminate the risk on Hong Kong Island, including buildings, infrastructure, distribution, population. Previously, GEO has constructed a very nice natural terrain landslide inventory, so we can see a lot of landslide on Hong Kong Island. HKUS did a little bit more. In addition to natural terrain landslide, we also added man-made failures, rainfall amount, and the consequences, so that we can identify the major failures in the past 30 years or so, and some factor building, distribution factor buildings are landslides, so highway network, and so each dot here represent a spot affected by landslide previously in the last 30 years or so. So step 2, we need to define the load. Right here, storm. It's relatively difficult issue. Of course, HKO, Hong Kong Observatory, helps. We like to define a plausible 4-hour, 12-hour, 24 hours for landslide, future landslide assessment. A relatively easy way is to make use of so-called PMP, probable maximum precipitation. So once we define maximum PMP, then we can consider several storm events. For instance, 44% of PMP, which actually was the rainfall event at Landau in 2008. Or consider a stronger event, which represent Typhoon Morocco, and even stronger event, which may not likely for Hong Kong, but we'll just take that for example. So then, of course, after define load, we need tools to analyze system response. So our colleagues at the USD are developing so both simplified program for larger scale catchment scale modeling and quite sophisticated CFDDA program for complex analysis. For instance, this example of a cell-based regional scale landslide analysis, and based on that, we may produce a distribution of landslide on Hong Kong Island under the real storm in the June 2008 event, and what if the Landau storm hit Hong Kong Island, and what if Typhoon Morocco hit Hong Kong Island, and even worse scenarios. We also have worked on distributed debris flow analysis programs, and so our goal is to integrate rainfall, erosion, initiation debris flow, and the movement, dynamic debris flow in the same package, something we call integrated analysis. So some preliminary results. So what happened if very severe event hit Hong Kong Island, and each spot represent a debris flow trail. Of course, if we just go particular catchment, we may also have more clear examination. So how many buildings or could be impacted by particular debris flow, and how severe the impact could be. So if we overlay those separate hazards together, then we just have a rough idea of what can happen on Hong Kong Island if the storm on Landau hit Hong Kong Island, and Typhoon Morocco, and even severe storm. of course, sometimes we also need to consider further cascading events. For instance, if during the landslide or debris flow event, if a particular valley is blocked, forming a landslide dam and the dam breaks, then perhaps larger area in the urban area could be impacted. So after that, then we need to quantify consequences caused by those multi-hazards, and using GEO's acceptance criteria to evaluate whether such consequences are acceptable or not acceptable. If not acceptable, then what kind of adaptation measures should be taken? Certainly, the multi-hazard risk assessment in such kind of urban setting is quite difficult. Just imagine, so suppose it's central Shanghai area, which could be hit by flooding, landslide, debris flow at the same time. So when we assess the consequences or the risk caused by such multi-hazards, we need to consider interactions among those hazards and interactions among vulnerabilities, because one element may be subject to several hazards. So one example of interaction among hazards could be well-known example of the debris flow which blocked the airport highway mentioned yesterday, right? So in that event, the drainage manhole was blocked by debris flow. In that case, then, so it's easy to understand why flooding, the highway was flooded together with debris flow. Now let me use a flooding example to illustrate the management strategy. So again, this was mentioned yesterday by Mr. Wang yesterday from DSD, Hong Kong Island. So before 2008, the drainage was mainly through stormwater system. Then afterward, the Western Hong Kong drainage tunnel was completed, and recently, so two detention tanks. So one on the Happy Valley, another Shanghai area, completed. Then we try to evaluate, how helpful those engineering measures are. So first, we analyzed the flooding case for the June 2008 storm on Hong Kong Island, and then try to validate our analysis result based on flood spots. Indeed, we need a lot more verification using more quantitative tools, for instance, flow rate, many other things. So many things to do. So after preliminary validation, then we apply the analysis tool to forecast what can happen. So for the flooding, so this case flooding depths. So during the drainage work phase 1, phase 2, phase 3, each phase, then we impose so the actual storm experience, the lentil storm and future storm. So we can also evaluate so-called hazard based on either flow depths or product of flow depth and flow velocity. So again, so phase 1, phase 2, phase 3. So this happened to be phase 3. Through such preliminary analysis, one observation, something like this, on the extreme event, engineering works are quite useful, but no matter what we do, the residual risk is huge. Therefore, no engineering measures are definitely very important. So after such preliminary work, we like to extend our work to entire Hong Kong. So Hong Kong we are really grateful to some of government department, DSD, GEO. So we are pretty privileged. So for such multi-hazard analysis, we are provided with, for instance, it's a very detailed distribution of urban drainage pipe, manhole, so all the underground system, so that we can integrate surface flow and underground flow in the same package. So some preliminary results for well-known Hong Kong Island, Lantou, and west-eastern colon, and New Territory area, particularly northwestern New Territory, which is a notorious flood-prone area. So following that, we'd like to extend further to the Guangdong, Hong Kong, Macau Bay area. This area was ranked number 1. So in storm surge, storm surge, and river flood. So in one of our assessment by a Swiss insurance company, so among the water metropolitans, this area ranked 3 number 1 among 5 perils, all 5 hazards. We don't, fortunately, not earthquake, not tsunami. So indeed, water-related hazards are quite important, very, very important for this area. So recently we just started a research on metropolitan hazard on the Korean typhoon and storm event for Shenzhen. And some more students, all here, you can see all here, start to working on landslide flood assessment for the entire Bay Area. Of course, at this time, or when we handle a larger area like this, 54,000 square kilometers, the grade is quite close. So we need to refine the course for relatively more specific regional study. For instance, probably smaller area, one analysis. So we're in the process of validating analysis and refine the urban studies at this time. So this is a case study looking at one of the largest storms in the recent 10 years or so in that area, 2005 storm, and so preliminary flood depth analysis and preliminary flow velocity analysis. So those studies are still ongoing, and so we do need refine our tools. We need a lot of validation, and we need to refine the description of the urban environment, which we found quite difficult. So that's the end of my presentation. So in summary, we'd like to propose a stress testing framework for evaluating effectiveness and bottlenecks of metropolitan infrastructures in the face of climate change. To do so, we do need very nice analysis tools to simulate multi-hazard process. Our dream is to eventually to develop a Bay Area metropolitan hazard simulator. We also need good tools to assess consequences caused by multi-hazard, and as case study so far, so we're checking climate change preparedness at increasing scales, starting from Hong Kong Island, then entire Hong Kong, then extend to Shenzhen and the Bay Area. So that's my presentation. Thank you so much.
Thank you, Mr. John. So we can take several questions from the floor for the 3 speakers.
Everybody's very shy. In that case, I better start. To warm the air up here. Maybe I would like to ask one question to Stephanie. Obviously, it's an extremely difficult job to coordinate such a huge project you presented. And would you like to share with us how to deal with all the stakeholders to get them all at the same pace under your leadership?
I'm not going to say that they are necessarily all in the same place. What has been useful is to have we've had a very long-term relationship with the key stakeholders.
So trust something.
So we started work on the first project called Bionics in 2004 or 5. And we involved them in the development of that project, and we've kind of kept them on board ever since. So that's you know, 14 years of working with the same organisations and increasing the dialogue. So we have regular meetings with them. They help us talk about our results, but then feed into the research and feeding in their problems, and gradually it's built up that kind of trust and relationship. And I think it's not a quick fix solution, but it's the way that we've done it.
Thank you.
Okay.
Yes.
One thing about Steffi's
Okay.
presentation. Yes, I think it's a great job, and also the recommendation about adding tow drains and drainage on slopes.
We all know this.
Yes, it's effective.
The thing is, I mean, it's not a new result. We all know the answer.
Right.
But I think it's kind of putting it in a way that the people who are going to actually look at the business case might understand, which is what we hear from our colleagues in Network Rail in Highways England, who are geotechnical engineers, who are saying, you know, we need persuasive arguments to get the investment.
And one thing from Hong Kong's experience we would like to share with you is that tow drains are really effective to sort of reduce infiltration into the slopes, and also sort of good drainage measures would help reduce the slope failure rate. But sometimes drainage without proper maintenance would be troublemaker.
Absolutely.
Yes.
And we could then, in our kind of scenarios, borrowing from your presentation, actually we could start to model out blocked drains. So with more sophisticated scenarios, that we could put drains in, we could block them, we could then look at put them in the deterioration or performance framework and do that. Yeah, sure.
So perhaps the asset owner may have a sort of aspiration that they may have a higher cost of maintenance in terms of their slope drainage. In Hong Kong's experience, this is true. We spend a lot of money in doing, not a lot, but we spend money on proper slope maintenance, especially before wet season.
Yeah, I mean, it's a good point, and it's something in Network Rail, the drainage organisation and who manages that is actually separate from the earthworks, and that's not great for this situation. So it's a management difficulty.
Yes.
Yeah.
Seemingly, everybody's still thinking, maybe if I may throw a discussion topic in a sense, because as we all, probably most of us know, one of the main objectives of this conference is to produce a policy. And so I just maybe throw this question to the audience, and say, with the context of climate change, we talk about in the future, all these predictions and so on and so forth. Would there be, will you support a policy, especially with government here and the industry people here, and would you support a policy saying, if related to climate change, government's contract, projects, has a certain percentage engaged in university? We won't debate on the percentage. Okay.
I don't think we're going to argue.
No. I'd like to hear from the audience. We have government people here, and the industry perhaps also I can see. I just thinking from a consultant point of view, I used to work in the London office. By the way, we talk about water. I still remember Duncan Nicholson when I was a graduate engineer, and he said to me, Charles, if we can solve water, all problems solved. I still remember that.
Who said that?
Duncan Nicholson.
Oh, yes.
Yeah, I still remember what he said to me when I was much younger as a graduate student, a graduate engineer. So, for young students here, solve water, done. Okay. Now coming back to, now I'm thinking about if I were a consultant engineer, obviously I would do all the job within my company. Human nature. Okay. So that's why we need a policy, in a sense. Even though I was talking to Anthony on the way here, even though I know my company capability cannot do a excellent job, but I can do a past job, I will still keep the job in my company. I will not hire you for sure. But you're too expensive, or I need to feed my own people. I mean, human nature, survival. Okay. And that is not the best for the interest of the entire society, or not the best interest of a country.
Perhaps in overseas experience, is there any sort of research fund, especially dedicated to the resilience against climate change? Is that kind of funding exist?
Or government lead? Good question. Yeah, government lead type of.
In EPSRC, there is, I forget what the program is called now. Is it Adaptation?
Adaptations, yeah.
So, yes, there is a sort of within EPSRC, which actually doesn't exist anymore, but it's the sort of Engineering and Physical Sciences Research Council. That had a program called Adaptation, Climate. I can't remember but yes, in
Similar sort of thing.
But
yes.
I suppose that the research council agencies,
Right.
they're self-governing to a certain extent, in that the policy is depended by the senior civil servants, I suppose.
Right.
And I suppose the minister can well have a say,
Yeah, I think
but
so.
they can have a say. But no, but
Yeah.
but effectively it's meant to be a bottom up rather than top down type of thing. But that said, I'm sure.
How about Syria these days? I don't know. In Syria, they collect money from industry and then.
Yeah, but that again, it's an industry. It's an industry to industry organisation.
Yes, yes.
Yeah.
But they collect money and then they give to Aero or give to
Yeah.
McDonald in the sense to do
Good.
specific
Yeah.
Type of research.
And they would also then always have an academic.
Yeah, that's why
panel.
I remember Robert Mayer, for example, led one project deal with tunneling related. So that is, so I could suggest in a sense with special type of arrangement. That Anthony, please take note because you're on behalf of us to make a presentation tomorrow morning. Unfortunately, tomorrow I won't be. I'm flying to Hangzhou this afternoon, so I think there's some sort of discussion. We're helping Anthony or helping ourselves in a sense to make things forward. I put the context in a sense under climate change because it's really advanced type of knowledge requires. We have to create new knowledge to combat climate change. Of course, existing knowledge help us, but okay, there's always a limit. So how's the time? Do we have a break and then come back?
It's quite flexible. If
Okay.
you don't have questions, then we can have a break.
No, there's question. Okay.
I have one technical question, not this question, to Professor Lim, right? I was wondering if you have considered another approaches in addition to the PMP, I mean the probable maximum precipitation, because sometimes it's controversial, especially on climate change. Because usually I think you define the PMP based on some the integration of water vapor, some atmospheric column, and when we see some rainfalls especially from hurricanes, like 1,000 millimeters in one day, it's like, whoa, it's huge. And you have like sometimes moisture transport, moisture flux. So some people say, oh, you cannot define PMP, or especially on climate change. And I was wondering if you have like tried different approaches.
So first of all, we use the PMP approach in a similar way as GEO and HKO's effort. Actually, Hong Kong's PMP was just updated in 2015. And the updating led to a significant increase in PMP, particularly, to us, a PMP concept has relatively clear physical meaning. For instance, when updating the PMP effort, first of all, we look at basic data from Typhoon Morocco. So we move Typhoon Morocco to Hong Kong, then rotate the storm to the topography of Hong Kong, because in Hong Kong, so basically our two highest mountains, aligned about 45 degrees. So we rotate the mountain, and then consider, then after that, then consider topography changes. Because HKO located at the Qiansha Zui, but then we need to modify the height, right? The location, the height of location. So after that, then consider some other amplification factors overall, then we produce relatively to us probably convincing PMP. At least to students, PMP is easier to communicate. If we use frequency idea, it would be quite difficult. Because the frequency, like 100-year, 1,000-year frequency, can be defined by 1 hour rainfall intensity, 4 hour, 12 hour, 24 hour. Well, in fact, in the last 10 years or so, we already experienced a few 1,000-year events already. This is quite difficult. It's quite difficult to communicate with the public. How come in 10 years we already got, say, 2,000-year events already? Something like that.
I was sort of supplement to Dr. Lima's the PMP study, the updating of the PMP study. I mean, the latest one was funded by GEO, and the whole set of results and the assumption behind. Well, there's a report published in our website. If you are interested, I can give you the website address.
So it's based on this yield gain things.
We basically make reference with the big or the intense rainfall events in our surrounding cities. For example, in Taiwan and in Macau and things like that. And then we transpose those rainfall patterns into Hong Kong with modification on the topography and as well as we rotate the rainfall profile so that there would be the maximum rainfall onto the land of Hong Kong, because within the Hong Kong territory there would be land and sea, right? And we try to rotate the rainfall pattern a bit, or to modify the rainfall pattern a bit, so that we can have the maximum rainfall hitting on the ground area. And then we establish this PMP, of course with modification and consideration with the saturation level in the air and things like that. Yes. And also assumption in there, we employ an expert from China, from Nanjing. Right. I can give you the report link so that you can.
Yeah, very good question. Follow on Carlos, yours. We discussed yesterday. I asked you a question, how to help you to help us. And maybe you can consider to get him to Brazil for sabbatical leave, 6 months. Okay. And our university is in some ways very generous. Okay. When he takes sabbatical leave, we still pay his salary, so you don't have to pay him.
That would be nice.
Yeah, that would be nice. Right?
Yeah, nice.
Yeah, I think, and also promote exchange between 2 universities or 3 universities in terms of students and so on and so forth.
Yeah, that's really
so Li Ming,
interesting.
on behalf of the university, I was highly encourage you to go for 6 months, but don't forget to come back. And I do have a question to ask Professor Griffiths. Again, he's traveled a long way, and actually he raised a very important question. That's why I will seek clarification. It's about swelling soils, expensive soils, and it's a huge business. I know in your part of the world, it's on billions of dollars. And what's the sort of feeling and what's the approach to combat climate change? Extreme droughts, for example, extreme wet.
Well, the wet, of course, there's swelling and shrinking in soil.
Yeah, exactly.
But the swelling ones cause a lot more damage.
Yeah, that's
the
right.
rain is
So what's the local government?
The strategy is just to make the foundations more robust. I mean, they're not trying to particularly solve the problem at source.
But robust, you need a prediction.
Yeah.
With climate change, we don't know what happens.
So even ordinary houses in parts of the Denver suburbs are on deep piers.
Oh,
Really very substantial
wow, substantial
foundations. And that's their short-term answer to solve the swelling problem.
I see, I see.
And they also have basement floors that actually can move up and down with the wetting. So that's a very pragmatic solution to the problem. Doesn't really address climate change, but I suppose the foundation can get deeper and more more substantial if, in the future. But, yeah,
So does the insurance claim go up?
Insurance claims are settled down now because they've realised
heavy foundation.
Because of that, yes.
I see.
Short term is much more sort of foundations you'd usually associate with a much heavier structure are now being used for residential.
That always includes cost as well.
You can always.
But people willing to pay something.
The house price increases.
Okay. Thanks.
Okay, so maybe we have 15-minute break, so then we come back for the other two presentations.
So come back. Why don't we make a comeback at 11? Right?
Yeah.
Because in 20 minutes and 15, no big difference. So come back to 11 sharp. I know you don't have time to reach. I try to.
How do we present after hazard, it's a group of 5 students. Then the second student start to conduct so-called risk assessment. For this group, we first look at really simple. And then potentially their factors. Before applying the factors, because once we apply that, it seems it's difficult for us to and first of all, numerical, still infiltration and yeah, still do that. Of course, the statistical part of that geo difference. So with the event still correct. But then we got make a cell. Then in each cell we know the number of slope features. And then in particular event, how many slope fail in that cell.
I think it was just a way of formalizing those features.
Right. Then we got so-called landslide frequency at that cell, because even in one event, the rainfall intensity is definitely but with assign one intensity for one cell.
因为看到前面有一个说这个绝对的变化，其实它会传播，然后另一个是它需要
but of course, so our landslide frequency analysis is some kind of annual phase, which is we assume landslide is mainly caused by one event, big event. It's quite difficult to separate within that. But indeed, it's rare that more than two events cause a lot of landslide quite a bit. Otherwise, it would be more difficult. Sure, yeah. That's why you really enjoy the talk.
And this is the humans are the same thing. They suddenly increases number of centrifuges from 5 to 6 suddenly.
看到还有发言了。
你比你师兄写的那真是这篇文章太短了。
Centrifuge in the world investing
他的写，其实我觉得他写的没有，关键是他整个文章啊，都是类，不是那种真的已经很差了，也不是很累，不是不累，但是是不是一篇值得
？It's a sort of national equivalent to US.
然后我再吐槽一下。
or we might say US equals customs. But still, US.
他那天也可以说，你可以这个事儿说了，你能说就这样。
Oh, there's a thing to say. Research thing is.
不是急吗？
我研究一下嘛。
那你看到网站了吗？
看到了。
那就下吧。
还没开始下。
那可以下吗？可以下。
That's why they work you guys.
Maybe they don't even know what questions to ask.
Exactly. When you learn to
go and have a coffee.
Yeah, I will go to washroom.
特别好，特别好，什么手机就感觉大家都做的很那个，但是那个 Tropical Cycle 其实有那个 JMA 的那个 Japan Meteorology Agency， 对吧？他有篇发了 Nature， 就那篇我们漏掉的。我刚才听他说他用前面些什么我没记住。TC 的反正好多都是在 Japan 的那个 Meteorology。反正在这我就感觉他说，哎，我们都做好了，挺好的。大家都肯定要这么说，挺好的。另一个那个，你不小心开到他肚上肥肉怎么办？幸亏当时紧急的收了一个。师兄有应急反应，刚开的时候赶紧收紧腹肌。师兄是我们中吃的最，除了内定之外吃的最少的。对，就他吃饭的话，然后水呢？谁？方费劲吃的最少。对啊，方费劲。他吃的瘦不一定吃的少，他吃的也是。
对，瘦不一定吃的。
那谁是胖不一定吃的多啊？
这玩意没有胖肯定吃的多。
胖不一定吃的多，胖真的不一定吃的多。It's outside. 我们走的。每天吃的跟猪一样。对啊，我妈说我就是吃面嘛，吃那个坛仔面嘛，吃那么大盆，然后吃的干干净净的。坛仔面。太热了，太冷我昨天回我办公室，然后就往那边回去嘛，因为周末不是不开这个 circulation 嘛，不是 circulation ventilation，circulation， 然后air 不能 circulate， 然后我就往那边走，我从25。往那个，我们是278对吧？25、26往那个278走的时候，突然很重的味道，那个车尾车，我就想这什么怪啊？然后越走越近就不对了，那个味道是很深的味道。然后你们怎么？然后我就发现味道越来越浓，我就感觉我就是在接近那个散发味道的中心。我一拐，有一个穿了那个，然后大胡子，然后在那打电话，然后他就站在我办公室的门口，然后我要回办公室拿杯子，然后从我要拐的时候，然后我就开始一直在屏住呼吸，然后我就一直头疼，我本来就头疼，我就屏住呼吸在那边。开门，我肚都是水，还开不开了？开了好久，然后继续，然后因为他在门口，我就觉得不要那么没有礼貌，我就还得慢慢走，慢慢走出来的话，我就拐过去，然后有意思，就是对，我知道好像是他们是不是那个，因为最近在有什么宗教的东西，所以他们不洗澡了。啊？不是有一段时间不能入院还是什么？身在戒佛。真的很重。听得太多了，有点害怕。
对你有想法就让你。
对我只有这句话要说。有，但我想喝些水。他讲的是 coastal flooding、coastal bridge 和 ocean 有关的。River Delta， 那也可以看。coastal bridge 在2。哎，你们那个Anthony， how can we pass you the note? Dropbox.
Email me.
So they will, maybe they can take a photo and then send you the.
But I assume your handwriting is good enough.
Very.
Okay.
Calligraphic.
Calligraphic.
I know. All my students are talented, multi-talented.
That's the interview, one of the criteria.
Yeah. They were like, when they interview, show me your calligraphy. 1 hour calligraphic test. 哎，你的毛笔字很好吗？
毛笔。
那谁之前毛笔字都没有。
你可以拿那种
钢笔。
就是有那种毛的那种，类似于。
毛笔加上水在地上写。那是小时候我也干过。我曾经练过，后来发现不行，是这块料。
下午来吧。下午那个 working 来了。
我还过来吗？
不知道。
弄过来了。
那 flopping 部分我就看了就发了。
因为没有什么 flooding。 主要都在那个就是 technical。我觉得你明天做的时候，做不是主要多说的就是 technical， 因为那边才好多 adaptation。flooding 的没有 adaptation。
就是那个政府他们。
对，只有 GOE 的 ，GOE 和不 GOE 啊，这 GEO 和那个 DSD 的，就是两个，就是 Raymond 和那个Adaptation。
可以提到了，因为那个刚才丽明讲那个 multi house。
那个但也主要在Landslides。
也提到 flooding， 我听到。
有 Landslide，flooding 就算这个，但是那个 multi hazard 它主要是说 multi hazard 是有 landslide 和 floods， 不是说有 floods and landslide。有一个 priority。
好吧。
还有一个吊杆。但是后面那个好像没有，不是你刚才说那个好像是你说的是 coastal flood， 那个宁波大学。吗？我就在2中那边。Identification。对，就是刚 expected article。然后，但是它也只是 identify the source. Most of the muscles they are originating subtropics and terminate in high latitude, including Western North America. Long AR events travel 7. No. 是但也有一点什么 long AR events travel 7 times longer intensity than short AR. 但是我觉得还是赶紧弄。你想找我？我在想我要不要去那个听那个。这就是那个，你看这写了一个非常strong的 reputation， 把你吹上台。我还有互补性。
Two more. Michael Davis. Okay.
He's the debriefing guy. Debriefing.
Oh, I see.
It's a kind of mixture of man-made and natural terrain. These days, Hong Kong has not much problem about the man-made slopes. Mainly concerned with the natural terrain.
Yes.
Bigger scale.
Oh yeah, that's quite factual. Man-made slopes and engineered.
Yeah.
Clever people have designed them.
Sometimes over design.
No, you don't design. You don't include suctions in the analysis. You kind of use it as a sort of bonus, really. If there's any suction, you'll take them. Charles gone now.
No, you'll be back. You'll be back.
I think he said something about lunch.
Yes.
Still on?
Yes, after, so there is, after this, after we can have lunch together with all of you, and then with leaving as well.
Okay, where are we going?
The same restaurant yesterday.
Oh, same as yesterday in the city.
No, in here, in the ground floor.
Oh, right.
The lunch yesterday.
Okay. The lunch yesterday, I understand.
Yeah.
Now, one thing I need to do is, I'm catching a taxi tomorrow morning, quite early, and I need Hong Kong dollars.
Okay.
And where banks are closed, it's a Sunday.
Right.
Because you pay the taxes usually with cash.
Yes, yes.
So I need to change.
How much do you need?
Well, I've got $151, and I think it's about $450 to $5.
Yeah, I think so.
So I need to change. I've got lots. I've got yuan. I've got Chinese currency, but I don't know if the taxes will accept.
I can do the exchange rate.
Oh, good.
I got a lot of
All right. Well, would you mind having Chinese currency?
No, don't worry. I used to.
So I could change, say, 400 or.
What about that? I'll give you 500. So I work out the exchange rate.
So this is a guy. I will put you in contact with some.
Oh, Yang Tongjiang?
Yeah. He's the organizing committee chair.
Of this
For this,
conference,
so you can keep this.
Okay, good.
So this is why we did it wrong. But I will email.
That's back here. This is the one meeting you're going to.
Yeah. This afternoon. But he's a very active one.
Okay, good. Well, I'd like to meet you. Thank you.
So 0.8x for the exchange rate, and then if I give, that means you just need to give me
440, right? Yes, I'll see you later. You want 440 Chinese. I've got it.
You said you have a startup company.
Yes.
No, I don't want to.
That's very
I'm not going to
good.
bargain with you for this exchange.
If you don't mind, actually I'm going to chair a
Thank you for
committee
being my
for newcomers. Startups. Yeah. No, seriously.
It's been very, very, very difficult.
Of course. But it doesn't mean you have to.
No, and it's not,
What's the schedule
it's
this
not
afternoon?
so much needed.
well,
They're pretty open, right?
It's the
I'm
trying
actually
to
asking because in the afternoon we're supposed to work together for the report back section. So I'm not sure whether the speakers, because we want to leave you for relaxing moments. I don't know whether
I think Limit had a plan, but I can't remember Limit Jan.
maybe bringing you
I may have done
This
that.
quick. We start somewhere.
Yeah.
Otherwise,
But I'll talk to
No,
Limit.
we're trying to.
So that is the sort of life arrangement, but for the conference itself, I need to confirm with Christine, my conference whether we need to sit together and things like that. But if not,
Our
then you
students taking lots of notes. I think we're taking notes.
that's our style.
so at lunchtime I'll talk to you. Thanks.
So we will finish our lunch at around half because
要不能复印你。Make sure won't miss your lecture. 多時間。
So the United States past that, run out of so you need to switch from grey
So welcome back everyone. So our next speaker is Professor Michael Davids. He's Pro-Vice Chancellor of Research at the University of Sussex, and his research interest is very diverse. It's including land reclamation techniques for soil reinforcement, slope stability, earthquake engineering, and also mathematical modeling of soils. So his work is very cross-disciplinary because he has been working with not only engineers but also with engineering geologists and also climate scientists and also biologists for his research. So he's currently the chair of the board of directors for Sussex Innovation Centre and also the member of the Greater Brighton Economic Board. So without further ado, maybe.
Well,
Good afternoon, well, good morning, still morning. Good morning, everybody. I'm not quite sure where I am, to be quite honest. Good morning, everybody. It's very nice to be here, and thank you very much for inviting me to speak at this workshop. What I want to talk about is some work that was done some years ago when I was at Dundee University, but just a sort of a new relevance, really, in the context of adaptation and resilience for climate change. So what I'm going to do is talk a little bit about, very, very quickly, because I think it's been covered by a lot of other people, about climate change risks to infrastructure in the UK. Saying, well, then how do we actually look into, I'm really sort of focusing here on slope stability issues, and what techniques can we use? And then as you can tell from the title of my talk, I'm going to focus in on two. And then really looking at then soil nail systems, and we heard from Dr. Quinn yesterday about how to add resilience soil nail systems are used. How can we actually assess these in terms of the climate change, and looking a bit at bioengineered systems as well, to see how they can help us, and hopefully can come up with some conclusions at the end. So if we start then with the UK sort of climate challenge, and we've heard a lot about this, I spoke a little bit about it yesterday morning, but basically we have these problems from flooding, from temperature, from winds, but heavier rainfall is what we're really concentrating on here, which can lead to embankment and slope failures, natural slope failures. So really that's what I'm going to concentrate on, and just rehashing one or two things that people have already said this morning is that the extended periods of rainfall resulting from climate change can increase the slope and embankment stability, and basically it's a significant road to infrastructure. So 2%, according to recent studies, 2% of the UK's network is at high risk of landslide, with a 6%, and that's a lot of the network. And as Professor Mendenhall told a few minutes ago, 50 landslides per year normally, going up sort of two per week, 100 a year in recent years, where we've had lots of extra higher rainfall. And so, and as Professor Mendenhall said earlier as well, the UK rail network is very ancient by most standards, and has 18,200 kilometres of cuttings and embankments, which many of which are at risk of failure because of the age, and the new climate signal actually will enhance the degradation of those. So really that's the background to this work. And a bit like Professor Griffiths, he's put down a number of things he thought about. I sort of thought, well, slope stability techniques, put out the undergraduate notes almost, and say, well, these are sort of things you can do. Regrading, drainage, we've heard about drainage being so important. Well, subsurface drainage, really very, very important. It is a theme. Get rid of the water and get rid of the problems, I think that's really important. We can look at facing, soft flexible hard surface facing, some for erosion control, some for stability, depending on the nature of the slope. Some retaining structures, gabions, mechanically stabilised earth, reinforced earth. We've got piles in the ground, micro piles in the ground. We've got ground anchors in certain situations. We're driving around here, see lots of ground anchors for certain applications. And then soil nailing, which I'm going to talk a bit about, and bioengineering techniques. So these are a range of things that one can actually use, but certainly for slope stabilisation, soil nailing and bioengineering are flexible enough for certainly here I'm concentrating really on what's going on in Hong Kong as well as in the UK. Just a little bit of philosophy, I suppose, and the approach that's taken in the research, and I think it ties in with things we talked about today, is that I'm going to be talking about sort of bottom left-hand corner here about physical modelling for work, physical modelling experiments. But don't forget, this leads into the whole what we're trying to do as researchers, and what I call integrated technical research process, where we do need to do field tests and field assessments. site investigation, we do need to do our numerical analysis, and they're all informed. You know, the philosophy informs our models that we might do. Our physical modelling informs development of numerical models, and indeed validates them. And indeed, I've used numerical modelling to understand what's happening in physical models as well, where things can be counterintuitive. So but what we're doing is to try and get understanding of the processes that are taking place, so that in the end of the day we can actually come up with designs and indeed reassessment of our designs with changing climate signals. So that's really my sort of philosophy to the design research process. So let's then move on to slope stability and soil nailing. In the UK, soil nailing it's very much from this stage. It came in as a retaining wall technique, really. And in the back, there's actually a retaining wall back. There's soil nails. It's a multi-grade junction. There's a retaining wall here. Back goes up to about 8 metres, and they're starting to build a new one here. A nice sort of stand on near the south coast of the UK. But really, you know, putting the nails in, shoving a facing on the shotcrete, and really, indeed, you know, the nice thing about this. You could actually be doing it whilst the traffic's still going on with what you've done already. So it's a quick, easy, relatively easy technique you can use. But it's very much a walling technique. And it wasn't until later, and well, there's another example here in Dublin Airport, an 8 or 9 metre high wall here, a wall which in fact is going to be faced then to form an underground car park. But you can still see here being used very much as a walling technique. It then became something more for slopes, slope stability, slope stabilisation. So actually come from South Wales. This is actually from around where I come from, where lots of rain and sort of and boulder clays, that sort of thing there. And you can sort of see here a very different type of technique, sort of steepening the slope, putting on a flexible facing. Not maybe as pretty a site as the one we saw previously, and you see the nails going in here at that site. So really sort of stabilisation and steepening of natural slopes. But what we found is that these are not without problems. And here's a soil nail system with soil facing, and you can see here in the next photograph where quite clearly through the design has not worked, and really it's what caused this. This is how I became interested in effective stress effects on soil nailing. Interestingly, the early days of soil nailing, and I know here in Hong Kong we've been much more enlightened, but a lot of the early work was all done on pull-out tests and total stress analysis, and I was a lone voice for many years in the UK fighting for effective stresses, and a lot of this work was based on saying you've got to do effective stress analysis. So work was done on the geotechnical centrifuge at Dundee, give an idea of the size and Tim Hughes from my former colleagues in the United States. And what we're doing is going to talk about some models that we've done. First of all, we're going to talk about some tests we've done on soil nails, and I'll talk a bit about some bio tests later. But basically, in effect, we're going to model here about a metre in size. We're going to build a slope in various stages in flight. This particular slope represents, in our models, these models, about 6 metre high slope with nails, 6 metre long nails in the slope. Regular, and you can see, and what we're going to do though is that we're going to start off with the water table here, and then raise the water table by raising the water table in the reservoir here, and to actually see what the effect is of rising water table changing the effective stress inside the model, and see what happens there. And I got this, and at the very end of the test, we actually inundated the top to raise the water table even further. So there's a water table level at the base, low water table due to drainage coming through, and then what I call inundation at the surface. And you'll see the measuring pressure. This is a typical nail. Basically, we've got it's drilled and grouted nail equivalent, 160 millimeters diameter drilled and grouted nail, which is 3 to 4 meters long. And it's strain gauge, so we can actually see the force in the nail. That's what we're going to look at. Here's a model with facing side off. You can see flexible facing there. Here's one with some soft set facing. It's a flexible facing one here, and just taking the side off and dug in a little bit. You can sort of see where the nails have been removed after a test. So this just shows I was talking about the water levels. So stage 1 of our test, and I'll be talking about these in a moment. Stage 1, 3. So it's 1 comes up here to 2, back here to 3, back here to 4, and then 5 when we inundate and the phreatic surface moves up. So we're looking at a cycle of water change. So what we're looking at is the bottom nail, the forces along the bottom nail in the system. And the line here gives us the forces at different points from the facing. And you'll see that if we just track the different tests, the sort of dark blue line I'm pointing is stage 1. At stage 2, as the water table goes up, the effective stress drops, so more force is taken by the nails from the soil. So the nails take on more load. We drop back. Interestingly, it locks it in. Which is sand here. It locks it in there. So when we come back, we go back up. It cycles. It basically ratchets a bit more. And finally, when we inundate, it goes up even more as more load is taken by the nail. So load's taking more the stabilising force as it comes as the soil stress strength is actually reducing. In fact, indeed, as the total stress is going up. Just looking at displacements that take place, and the horizontal displacements here in the bottom line, and you'll see that these are actually in prototype scale, so it's 15 millimetres, maximum 25 millimetres. So we're not talking huge amounts. We're quite a long way to failure. But certainly, if it's a slope, a natural slope, not a problem. If it's a building on the top or something like crack, then obviously it does make a difference. But certainly, we can sort of see how we raise the water table. We lower it again, we raise it again, we raise it again. You can see how that affects the displacement of the structure. It's moving, and it has to. The nails to actually work. These are passive inclusions. The nails to work, there's got to be movement for the nails to work. Otherwise, they don't. This shows them for the whole series of nails from the top to the bottom, and it shows different stages in the test. And you can see that this is the peak force in each nail at each stage of the experiment. What's interesting, for more observant, is that as we've gone 1, 2, 3, 4, and then 5, it drops back. Now it's taken on the nails are actually the peak stress has actually gone up the bottom of that bottom nail, but actually above there, actually the force of the nails drops back from the penultimate stage. So scratch my head quite a long while about this, but in fact there's a redistribution of force in the one. If you actually normalise each nail maximum force by the pull-out for that nail, you'll see that the top one is actually, it's about 0.8, probably gone over the peak. That nail is probably pulled out. Now still, because it's a frictional material, it's still holding on in there. It's gone over the peak pull-out force and effective stress because there's still a force there holding on to the nail, stress to the nail, and there's been a redistribution. So throughout the structure, the nails are all well below the pull-out band. So the stability is still there, but the top one is probably close to failure. And you can sort of see. From the analysis, really, the simple Bishop analysis, where we looked at the restoring and the ratio restoring moment, disturbing moment, basically. So it's a basic factor of safety. And at different stages in the experiment, you see that even at the end of as we raise the water table, the factor of safety, we like to call it that, reduces, it rises, and then it comes back down. So at the end of the test, we're still, as would be determined by the relatively small displacements for failure displacements, we're quite a long way from failure in this case, but you can see how the behaviour has changed in cycle wall. So now we move on then to bioengineering, and really what we find is that vegetation can enhance performance of our slopes, and for a number of ways. First of all, see here's controlling erosion, and that's one of the major reasons we use vegetation, using vegetation as the facing for even the soil nail structure. So basically, it provides that shielding of the surface. Indeed, a green finish, for example, which you do here, I know, which you use more and more in the UK, to the facing is in fact a soft facing with a green finish. Another area is through evapotranspiration, reducing the weight of any potential unstable mass of soil, indeed, and that also causing a high negative pore pressures as it sucks in, and acting obviously, as we talked about before, in previous tests, that causes negative pore pressures, which actually enhance the strength. But just in that sense, with certain deciduous plants, come the winter when the leaves fall off, and in the UK that's when we're expecting more rainfall as part of climate change, you lose that suction for that particular time. Now, if you have evergreen plants, it's a different issue, but certainly you lose that suction from deciduous. But what it does do, though, even to that cycling, is that as it sucks out the moisture, as it reduces the pore pressures, that causes the soil to consolidate. And so you're actually, through those cycles, you are actually over-consolidating the soil. Actually, you're not normally consolidating, but as the pore pressure changes, you're over-consolidating. So you're actually stiffening generally as the soil is taking place and strengthening it. So it is having an effect, even though the other effect of having the negative pore pressure there permanently isn't when you have to rely on. You can rely on the strengthening effect. And finally, last but maybe not least, last one to look at really is the mechanical strengthening of the root zone system. So that's what you can rely on until the plants die. I've taken out the slides. I did have you show what happened to the plant die. Because basically, the plants die, then in fact very often that will then form a preferential path where the roots have died off for the water to go through and get down to where exactly it wants to be on any potential shear plane and actually increase the pore pressure. So maintenance, like everything else, is really, really important when you've got these root systems. So just to look at sort of shallow landslides from the Eco-Slopes project that took place some years ago, and you can sort of see below the tree line that the slope in London clay is failing. If you dig down into the slope, you can sort of where it is there, you can see roots there going down to about a metre depth hole, and you can sort of see exposed roots there, which are acting as sort of reinforcement to hold the slope together. This is a sort of this is a fir tree. You can sort of see the root system here. Now, what's interesting is these root systems, they are they're quite lateral, they're quite superficial, and basically look at the data. Versus for a black willow tree, and typically within the top 1 metre. Now you can get taproots that go down deeper, and so not all trees are the same. Different species with different taproots. So root distribution tends to be the majority in that sort of top up to 1 metre. You can get down to 2 and 3 metres, very below that. But certainly you can use sort of like this concept of an analogue between roots and soil nails. Yeah. And so basically, if you're thinking of stabilising as a soil nail, the mechanical stabilisation, you've also got vegetation, which can act in a similar way from mechanical. And so as a sort of geotechnical engineer, looking at this, I say, well, look, how we can treat roots in the same way as we might a soil nail in a mechanical way. So we started off by, well, let's have a look at the actual strength of roots. What are the strengths? And my colleagues and I developed in Dundee at the time probably the first ever real testing of roots, because people have been testing roots for a long time. But they were testing and they were looking at the global displacement of the roots and coming up with the strain. But as we all know, you get necking when things take place. Failure will take place in a localized area. And so we actually applied the technique of PIV to actually measure not only the image analysis, not only to measure the strain very locally, so we get that very local displacement strain, but also we can actually look at the Poisson's ratio effect, if you like, and measure the diameter change as well. So we have really, sort of great PhD students and postdocs working on this. So I wish I could claim all this for myself, but they're really, really good. Worked very hard and getting some great work done in this area. So as you come up then with the strength, and then on the left-hand graph we have basically shows this tensile strength. And what struck me, as somebody coming into it, not somebody from the vegetation sort of side, from the civil engineering side, a tensile strength of a small, very narrow, small diameter root is almost the same as steel. 207 steel, something like that, along those lines, megapascals, and we're getting up to, the small ones up to certainly over near 150 megapascals. The stiffness is very different; it's about 100 times less, but we're still getting, 2 gigapascals of stiffness. So it's amazing. It's actually amazing when I first saw this data. So we can start thinking of these in terms of an engineering material, albeit a natural one and very variable. So in order to do experiments, we run experiments with analogues as well as real roots, and because of the variation, it's quite difficult to come up with ideas, fundamental studies on real roots. So we looked at analogues, and so we looked at sort of three different architectures: the tap loop, the herringbone pattern, and the dichotomous. And then we did sort of pull-out tests on those, and you can sort of see the pull-out when we do with sort of a normal sort of nail or anchor, and you can still see that the dichotomous gives us the best pull-out water. So those are the ones we concentrated on. And so we ran tests with not both at the same time. This is for explain how we did it. Some with roots, real roots. Some with the analogues. We ran this about 15 cubits smaller, still 6 meter high, but root lengths were up to 1.5 meters in depth. So we're looking at 1.5 meters maximum depth of penetration of the root. So here's this shows some of our willows growing. We did 2 different age willows. Not the most successful test, I have to say. The roots at a young age were not terribly good. So we did some longer ones, but tying up an expensive centrifuge box for 290 days is not something you can do that often, and it also is a lot of time. You don't get many PhDs for 290-day tests, if you know what I mean. The PhD students will appreciate. So these were really done towards the end of our work, just to see what if. And most of the work, to be quite honest, was done using the analog. But nevertheless, we had some interesting results, and Sonnenberg did some fantastic work in this area when he was working in this area. So what I'm showing here is just to look how the effect of these roots will change the failure mechanism. So we've got here what we call a fallow slope, in other words, there's no roots in there, and on the right hand side you've got a cross section during flight in a centrifuge test. On the left hand side we're looking down the top, so you can sort of see the failure taking place. So if everything is working, then we can sort of have a quick look and see what happens, and you can sort of see how it fails from the base. And we get quite a translational slide come the end of up to the start and coming back. And what's interesting, if you weren't concentrating on the picture on the left, which we'll look at that, if you look at that, you can sort of see that it's sort of developing almost into sort of flow slide. There's a lot of water coming through, begins blocking failure, and it's sliding away. But basically the thing is breaking up as it fails. So if you move on to slope. Now what we've got here, just to quickly explain, we're looking at a section where we put some on the side of the box, we put two types. First we've got nails in there, and we've got some which are, basically these are all dichotomous nails. You can just see the roots based upon root systems. These here are actually series of, something I picked up from the geologist I work with, basically series of little columns of plastic tubes. You put the whole pile of plastic tubes onto a rod, you put it in the ground, you remove the rod. So basically, little sections, you actually buy them in Toys R Us actually, and then basically so you can see where the failure mechanisms take place. So here we go again, and you can sort of see here that with the root systems in, that we've got it holds the blockage together, and you can sort of see here quite nicely the root to the dichotomy starting to pull out, taking place here again. But it certainly holds the whole thing together. And here are from PIV analysis. You'll see we've got initially as the starting to get the slope, as the toe starts to go, you can sort of see the formation starting the formation of the failure, eventual failure surface. Here, this shear plane is quite developed. You can see actually these are the movements around the bottom of those dichotomous roots, and this is the final displacement at the end of the experiment. And this is all really good data that you can actually compare directly with that. I know that there's some Anthony's been doing subsequently, which is really good. So that gives you an idea, looking at the slightly different in failure surfaces. You've got the root systems here. We did some taproot test as well. Finally, we just looked at the factor of safety that we got, and the root area ratios here, given here with taproots and dichotomous roots, you'll see the factor safety of 1. Basically, if you ran an Bishop analysis and we didn't take any consideration of the roots at all, at failure, we'd have had it was telling us that these were about the taproots and say the dichotomous roots about 0.8, 0.9 factor of safety. But in fact, the factor of safety was actually 1. So what we did was we calculated what would be the extra cohesion resulting from the roots to bring it up to 1. And we saw that these were, you can see the numbers here, about 0.6 kPa, 2.7 maximum. So that would be the extra cohesion that those roots are giving. Now, interestingly, we worked from our pull-out test. We actually worked out what the pull-out would be, and it's not a million miles away from where the pull-outs are. But a lot of the literature was saying we should be using the tensile strength of the roots, not the pull-out. And those at the bottom line are the tensile strength of those roots, which are way, way ahead about what we're having. So which basically they say, look, you can rely on the pull-out, which you have to be able to calculate, but you really can't rely on the tensile strength. So basically, to come to some conclusions, first, fundamental studies using centrifuge model can actually have really good insight into the change of effective stress. And really, this is how do we actually develop our, well, how can we assess current structures to see how they're suitably resilient for changes in climate, and indeed in our design view as well. So it allows us to assess what we have. It gives us orders of magnitude, we come up with mechanisms, you can do qualitative analysis, which basically have to understand what's taking place. And you can use that then to start informing numerical, analytical techniques. And so we've got that quantitative data as well that we can use in validating analytical solutions, be they Bishop or the sort of stuff that Anthony's been doing more recently using fine dynamic analysis. And so really, I think what they do show is that these techniques do allow us to have a much better idea of what happens when the effective stresses change in these reinforced slopes. Thank you very much.
So before we talk about the Q&A, we have another speaker, Professor Clarence Choice. I have his CV on my phone. So he is a research assistant professor in this department, Department of Civil and Environmental Engineering, and also he is the junior fellow of the HKUST Institute for Advanced Study. So he is now the chair of the International Debris Flow and Steep Creek Hazards Mitigation Committee of the Association of Geohazard Professionals. So we have Professor Choi talk about something about landslide, debris flow, and also the recent technologies of mitigation.
Thank you. Right. Yeah, thank you for inviting us to share our project. I'm presenting today on behalf of Professor Charles Ng, and there's some collaborators on there. You'll recognize Julian, so please don't shoot the messenger. Right, so some of our collaborators are at the bottom of the slide here. And I'll start off today's presentation by sharing with you a bit about landslide mitigation using physical countermeasures. And then I'll draw some scientific challenges based on this background. Then I'd like to share the new facility that we've developed as part of this ongoing theme-based project. It's a large-scale flume in Hong Kong, and I'll talk about how we plan to use it and how we will use it to develop some guidelines. And then, of course, I'll jump into the main part of this presentation today, the multiple flexible net barrier system. And we'll talk about how we characterize the impact load, discharge. I'll summarize, and then we'll look ahead to see what we plan to do moving forward. I realize now that Julian and Professor Li Mingjung have gone over some of this content, but I do still want to show some of these short clips highlighting the threat posed by landslides. So this
바로 앞에 있던
is
차량들이
in Seoul,
순식간에 사라졌습니다.
catched by a dash
일속
cam in
직발의
a car,
순간
about 4,000
여신은
cubic
급히 제동
meters
장치를 밟았고
debris. And we have another one here in northern Taiwan, in front of a debris torrent, and we have a massive 115-ton boulder, almost crushing that car. And then another one, more global relevance in San Bernardino. This is a debris flow that resulted in 2 fatalities. This is a post-forest fire debris flow. And lastly, some local relevance. We've been talking about this a lot, the rainstorms that pounded the Lantau Island. And this is about 400 cubic meters, so we blocked the road to the airport for about 16 hours. So now that I've shared with you a few clips about the threat posed by landslides to infrastructure and human lives, I want to draw some parallel to the theme of this conference. So we've probably heard about these from Julian and Professor Jung already. So this is essentially a forecast of what could potentially happen in terms of density of landslides if rainstorms, historical rainstorms, were to hit Hong Kong Island. So of course we have the 1966 rainstorm. Well, this did hit Hong Kong Island. There were 64 fatalities, and there's a nice little photo at the bottom of the slide here. The next event I do want to talk about is, well, the 2008 rainstorm. So this is again forecasted as if it would hit Hong Kong Island. That's the density of the landslides that would occur. And another notable storm, extreme weather event, is typhoon in Taiwan that we talked about already earlier in this workshop. And I guess I don't really have to connect the lines together, but I guess you can get my message here. So the question is, how do we enhance our resiliency against these extreme weather events? Of course, the focus of today's presentation is on physical countermeasures. What we see on this slide here is a single reinforced concrete barrier at the base of a slope. Just for reference, if you want to gauge how big these things are, you see a double-decker bus at the bottom of the slope there. And so this is on the way to the airport. You probably can't see it because it's covered by trees, but it's protecting you from debris flows. A problem with single reinforced concrete barriers, they're quite large, massive. They are built near the road because we do have to clear them out afterwards, and they impose surcharge loading, and we try to install them further upstream. A little counterintuitive when we think about it, because we allow debris flows to pick up momentum and entrain, reach larger volumes, so the scale of these barriers become quite large. So as part of Professor Moon's theme-based project, we're examining a new type of countermeasure. How about several smaller flexible net barriers in series? So this is actually a similar catchment, I guess. It's the same catchment. So what if we installed multiple flexible barriers? And what if we installed flexible barriers upstream that are more pervious, because we can't get up there anyways, we can't maintain them, and once they fill, they're probably going to corrode and cause problems. And then downstream, we can catch all the debris here, and we can still remove it. And we can progressively attenuate these debris flows. So, what's the advantage of flexible net barriers? Well, these kind of barriers were originally used for rockfall protection. Essentially, we want to prolong the impact duration so as to decrease the forces. And we all understand this from impulse momentum theorem. So it's quite easy to understand for a rockfall scenario, but how about for debris flow? Well, if we look at measured data from some of our experiments, these are from centrifuge model tests, we see that flexible net barriers for debris flows only have to absorb about 15% of the initial kinetic energy. This is very different compared to rockfall barriers. This is because debris flows comprise a granular assembly, and essentially you want to mobilize the shear. And it's a very frictional type of flow. Maybe that's why they use sandbags to stop bullets as well. So this is the special feature of flexible net barriers, and also do notice that they're very much pervious. And the more pervious a barrier is, the lower your impact force will be. So how do we predict the impact force? So we use, well, conservation of linear momentum essentially. And we include an impact coefficient, which is shown in the red on the slide. There is some theoretical basis to this impact coefficient. If momentum is destroyed at impact, of course, it's unity. And of course, if momentum conserved, it's 2, which should be an upper bound. but obviously engineering is an art as well, and we have a wide range of impact coefficients in literature that are mutually inconsistent, but I'm sure they serve their purposes as well. So, in essence, how do the effects of deformation in the pervious net influence the impact load? We've already begun developing frameworks for multiple barrier systems as part of this project. These existing frameworks are from Julian and Professor Wu. They focus on rigid barriers, and now we're progressing towards flexible net barriers, which are different animals. So, based on that background, I'd like to draw some scientific challenges. Essentially, for this theme-based project, we're looking at what are the mechanisms of interaction between debris flow and multiple flexible net barriers. There's several problems we have to look at. These are pretty dumbed down, I guess. How pervious should a flexible net barrier be? It sounds trivial, but it's not so trivial. How much deformation is enough, and how far should barriers be spaced? So within the constraints of this presentation, I'm going to focus on the pervious nature of a flexible net barrier. So to achieve this kind of research, we all know debris flows are a scale-dependent phenomena, and we need the largest testing facilities possible. So, we're fortunate enough to have collaborators at the University of Hong Kong Kadoorie Center for this nice piece of land where Professor Charles built a 28-meter long flume that can retain model 10 cubic meters of debris flow. So what we see at the top here is a storage container where we put the debris flow, and there's a double door system. It's watertight, essentially to simulate dam break. And we have a transportation zone here, about 15 meters, inclined at 20 degrees, and then a horizontal runout zone. Within the channel, we have all sorts of instrumentation, which I'll discuss in the subsequent slide. So, of course, we'll measure pore pressure using pore pressure transducers. We'll measure normal and shear stresses using triaxial load cell. And, of course, through the normal stress, we can deduce the bulk density of the debris flow. And of course, we have other instrumentations as well, high-speed imagery. We do 3D reconstruction, UAV, smart particles, and just want to give you a sense as to what we're capturing. So, back to the focus or the content of this presentation, we're modeling dual flexible net barriers. So essentially, I'll talk about 3 sets of barriers here. It's quite simple. We have our mesh opening here and characteristic particle diameter, which is just a D50 in our case. And at the upstream barrier, we vary the mesh size. It's instrumented with tensile load cells on the cable. And the downstream barrier is here, and we keep the mesh size opening the same. For debris composition, we carried out a quick literature review of existing debris flows around the world, just based on their sand, gravel, clay, and silt content. And then we characterized debris flows in Hong Kong, thanks to a report by Eric C. And basically the points in red are flows reminiscent of those in Hong Kong. And based on this kind of study, we decided to characterize our flows here, where this yellow star is shown. So I want to give you a sense as to how these tests work. So let's focus on the top left of the slide here. So we've put our debris material in there. There's about 3 cubic meters in here, and we have a specially tailored design, custom-made gate to initiate dam break. So once the debris flows downstream, and then I'd like to transition to the bottom of this land here. So we're looking downstream of the debris. So that's the first barrier. It piles up. And you see here a brick here. This is a smart particle. And then here's a bird's eye view of the same test. So you'll see both barriers in action here. The first barrier is located here, and the second barrier is here. You see that it's moving because we're using a UAV, unmanned aerial vehicle, to capture this. So that's a typical test, and that's our new facility to study flow structure interaction in Hong Kong. Right, so now that I've shared with you our background and methodology, I'll jump into, I guess, some results. So based on our test, this is captured from a camera right above the net. We noticed some interesting things. During the flow process, we see the continuous formation and destruction of arches at these openings. So in order to revise or enhance the existing state of impact load prediction, we do want to capture this mechanism. So the best way to do this is to look at what physicists have done. So we like to borrow the Beverly law for this, which describes the formation and destruction of arches at openings here, essentially equating a free-falling particle within an arch and modeling it like this, and this is what we get. And there's two shape coefficients, so I guess you could say it's semi-empirical. So that's the discharge. Now, once we know the discharge, we can adopt well-established impact models on rigid walls, which is shown here, and we can take a two-stage approach based on conservation of mass and momentum and a granular bore for well-recognized impact models for a rigid barrier. And we plug in the Beverly law to account for the discharge to the net. Then we get a modified impact force equation here. So then once we know this, then we can use our large-scale data to evaluate the performance of our new impact model for net barrier. And I've made it as simple as possible. So here is the normalized impact load. This is basically the impact coefficient. And on the x-axis, we have our mesh opening normalized. The blue line is our new analytical solution, and the red dots are measured data. And we can see that with our new analytical solution, we have an upper bound, which is good news. And we'll look further into this, of course. So aside from the impact load, we also want to look at the discharge to the net. So we carried a lot of flume experiments, and we used it to calibrate a discrete element model. So you see a physical test here. This is a small scale, and this is our discrete element model. So what do we use this DM for? Well, we use it to study interaction between particles and apertures. So in this case here, we have a vertical slit. Of course, we can study horizontal slits. We can study nets. And why do you want to do this? Well, we want to look at the trapping efficiency of these structures. So on the y-axis here, we have how much volume is retained. And we know that all impact scenarios are a function of inertia and, well, a Froude number, essentially. So with different S over Ds, we get our design charts as well. And what's interesting with this is we see a very steep region here. And this steep region constitutes a very unstable region where stable arches cannot form. And if we want to develop a self-cleaning barrier, we want to model or pick our S over D ratios where this region is very unstable. So if we implement and we put all of these findings, then we can see here, this is a very coarse net. You see that it breaks the energy for sure. At the same time, it lets all the debris flow past. So this is a barrier located much further upstream. I'm not going to show the video, but the entire video, but eventually all the debris material passes, and we can sort of control the discharge. And we have a system of barriers that essentially we can look at the performance of the entire system. For example, I tried to simplify as much as possible in a bar chart. So what we see here are three sets of blue and gray bars. So this constitutes the first set of dual barriers we modeled. This is the second set, and that's the third set. So based on the principle of trying to minimize retention further upstream, then we want a decreasing, or increasing, sorry, normalized volume retained. So this is just one aspect we can look at. These are preliminary results. We just finished these tests recently. And of course, for example, this upstream barrier is overutilized in this case. Right, so I'd like to draw a summary. So essentially, for this project, we're using physical models to develop new impact models so we can investigate multiple flexible barrier systems. We can evaluate them, and we have different models in the centrifuge, small scale. We can do a multi-scale approach, and we can enhance existing guidelines. And one of the products or aims of this project is to develop a set of world-leading design guidelines for multiple flexible barrier systems. And of course, this can lead to cost savings and more sustainable development against debris flows in mountainous regions around the world. Lastly, looking ahead. So debris flows are scale dependent, and I guess it's trivial to say this is a large scale flume, because what is large? Debris flows can be million cubic meters, but Professor Charles spearheaded one of the, I guess this will be the world's largest flume model. 500 cubic meters is how much is the volume we can model, and we'll use this facility to model flow-bearer interaction, develop international design guidelines, and to test basically our tech transfer. What we learned from our research, we can apply it and test in this flume as well. So our collaborators, the Institute of Mountain Hazard and Environment, and this facility will be in Kunming, China, beside the existing debris flow and observation research station. Some other aspects we're working with Geo and Julian on, in particular, are smart impact switches. So essentially, once a bear is impacted, we're notified of this, so it doesn't overspill or potentially serve as an early warning. And we're working closely with Geo, the Jockey Club, Professor Chen on this issue as well. And this is just a video of us evaluating weather hazards using large-scale filters installed on a rigid bear. Try to keep it brief as possible. Thank you for your time.
Thank you, Clarence. Q&A time. Questions from the floor? Yes, please.
I really enjoyed your videos of the flume. I wondered, maybe I missed it, but obviously the flume experiment is quite a smooth base compared with real life, I guess, when it's tearing its way down a hill through vegetation and maybe rocky places. Are you going to somehow take that into account, remove that, have some frictional correction factor or something that might help? I don't know if it's important.
You're right, erodible beds are very important, but I guess for our research we're starting with non-erodible beds first.
So you could roughen up that base later on?
Yeah, we could roughen it and even put a trainable bed in later on.
Good.
I guess we barely scratched the surface.
Yeah, just started.
I guess Professor Charles.
Maybe I'll add something. Definitely, actually, CARe is too humble. Actually, I flew 10 PhD students on him, and he take care of the 10 PhD students, do all the work. He should take all the credits. And also, I'd like to add Stephanie's comments. He said, long-term trust is very important. And thanks to Julian. Without Julian, this project is not possible too. And I think when you were a little boy at the time, collaborated with W.K. Poon. Yeah, little boy at the time. W.K. Poon now is the head of GEO. When I returned to Hong Kong in '95 and started collaborating with GEO, it really took a long time to build the trust and collaboration. And thus I echo what you said. I think when we talk about climate change, I think we need interdisciplinary and also interdepartment and industry and academic to collaborate. I think certainly I echo that. So going back to your question in a sense, it's actually the right question. But we think about we start from conservative, nice to be conservative first. So a smooth phase is going to be conservative because no energy is dissipated. Yeah. So, but later on, obviously we need to refine. Just like your case in Colorado for expensive clays or expensive soils in the sense. I was thinking, yes, you can put whatever heavy foundation there, but it's going to be very costly. Of course, it's conservative. May that be too conservative? And this is why, actually, perhaps you know that using rigid and fragile barrier around the world is not new. Okay. And actually, we talked to a supplier, okay, a fragile barrier supplier. They came to our campus. They said, "Why are you guys doing multiple barrier research? Why don't you put this everything same size?" Of course, from a manufacturer point of view, of course, you put it as big as possible. That's great. Okay. And so actually, in some way, we are trying to improve our understanding and also improve our design. Instead of putting one big barrier, multiple, and of course the question is, what's the spacing? How big, how high? And do it in an economical way. And Hong Kong is relatively small, it's okay, even though we are waste too much money. But when you're talking about Belt and Road countries, that's a huge, long distance. And obviously, people are going to build roads and railways, connect countries. Go for mountains is unavoidable. How are they going to prevent that? And that's why in our research group, we have students from 16 countries, and a lot of them are along Belt and Road countries, Pakistan, India, and so on. And this is a paper way to sort for future, in a sense. But no matter what, all the work done by parents, I have done nothing. I do the talking and he did the work. Just that. Okay, so that, but anyway, by the way, he's on market. If anybody wants to grab him, quick. And by the way, we have some brochure. I gave some of you here for the theme-based project. As I guess, if anybody wants to take a copy, well, I done it back there. Anyway.
More questions?
If I may, I do a question to Michael. Actually, I would say thanks for your sort of initiative to use centrifuge to model plant. I might say, and now I can say actually all your papers reviewed by me at least. I'm one of the reviewers. Not got published, so I can tell you. I mean, very intriguing type of experiment. And one thing I think very often we sort of forget in some way. I still remember when he was a PhD student, one day he came to me saying, why we want to measure suction up to 1 MPa? Normally suction will need 20 and 30 kPa. Remember that? He brought me to my office, I can't remember where, but he brought me to me saying, why? Okay. I said, you think about for unsaturated surface slopes, and permeability is not constant. Unsaturated is dropped substantially. So when you go to high suction ends, means over 1,000 kPa or 1 MPa in the sense. And actually, the order of magnitude, at least 3 or 4 order of magnitude drops. So then I said to him, I said, look, the purpose is to prevent infiltration, minimize infiltration. I wouldn't say prevent, minimize infiltration. And we discussed this morning already. If we can get rid of water, then we'll solve the problem. Okay. So I think in your test, you deliberately plant those that take 200 something all days. That's right. And that's why recently, actually about 4 years ago, 5 years ago, and we had a collaboration, and then which we actually developed a I would say it's a pump, if like, okay, try to simulate transpiration of plants without waiting for us 200, 300 all days, so they can simulate the effects of transpiration, hence increase suction, so they minimize rainfall infiltration to the slopes. Of course, it's sort of not genuine like yours, and, but I don't know how do we see future. Okay, this future meaning I know it's difficult. Same as Hong Kong in some way. Okay, to promote more use of natural material like plants.
Well, probably something I'm looking at.
Yeah, both of you, as in somewhere. Maybe the question is for both of you.
In the UK, it's difficult because any innovation is quite difficult to transfer into practice. And I think there's been a case recently looking at failures on an inquiry into some failures on Network Rail that has thrown up the issue of vegetation. And Network Rail did have a program of clearing vegetation from close to the track, which was then questioned by this inquiry because of the beneficial effects of the vegetation. But it's again the Network Rail, the vegetation management people are different from the geotechnical engineers. So it's kind of getting the two teams to talk to each other to get that work going. But I mean, in the case of Network Rail, there's lots of vegetation already there, so it's maximising the value and the benefit from what they've already got, and to make sure that they don't take it away first, and then using that perhaps to sell the beneficial effects to other places.
Yeah, I first started working on this vegetation when Network Rail started this work on irrigated slopes. And anyway, in the UK, there was became sort of national joke about leaves on the line. So basically, during in the autumn, before basically the leaves on the tracks, the engines couldn't get traction, and so it's bringing the rail network to a halt. And so they decided the way to solve that was just by taking everything. And they had these what they call 6-meter flail strips, where they just took 6 meters at a side to stop, to actually get rid of the vegetation from the side. And that was that. Then the concern was, well, now your vegetation is dying back. And I mentioned earlier, it's that you're actually not only removing the stabilization by having negative corpus, but also if all of a sudden you've got roots which are going to bring water into the ground, which are making the mass even worse. So it's this balance between contraction and actually work. So what we were looking at is other plant species which don't give you the leaves but go into the roots. I think that's not that's still work in progress, but that's not an impossible task.
Yeah,
so actually, there's so to different types of species to keep but it takes a long time.
Yeah,
to keep the change.
I have to share with both of you actually. Recent work, because after Anthony will continue to work this area. And what we find actually, of course, in the literature, the people talking about roots bringing water. Actually, it's not true. When the root is life. Yes, only when it's dead.
When it's dead.
Yeah, it's dead.
When it dies, it dies back.
Then dies.
So it came back and it dies.
That's a sort of problem. And I don't want to keep you only listening there, and maybe he's the expert in probability, reliability.
I'm all right listening.
So bring a discussion that I don't know whether it's right or wrong, but also it's a sensible approach. And Li Ming, of course, is here. We cannot design everything perfectly safe. And it has to be reliability based.
Yeah.
Okay, nowadays, and in traditional from structural, now it's called the geotechnical in a sense. Now, what about risk? In a sense, and we are two risk experts here. And again, if say increase probability because of dead wood, okay, we are dead people in university very often dead wood.
Hopefully not.
Hopefully not, but we do. Even USD will have quite a lot of dead wood. Anyway, so how to? It's a sensible approach. So moving on to risk and reliability approach to bring in vegetation. I'm sure governments, for example, rightly so, they're cautious about root structure. Rightly so. So how do we move that? Yeah.
Well, I think there is some research and publications on probabilistic treatment of root reinforcement, for sure. I think there's more to be done there.
Yeah.
With random fields or even simpler.
Yeah. Less restrictive, otherwise those predictions, they say, oh my God.
Yeah, it's frightening. Yeah. We don't need to alienate the practitioners, but I think you're right. There's no such thing as zero probability of failing.
Actually, I learned from you, know that.
Consequences are the thing,
Yeah.
and then from there you have to have a target probability of failure.
Right.
It's an acceptable one to the community.
Yes. I don't know, Li, do you have anything to add?
Yes, certainly I agree. So if we bring in some relatively based design, perhaps we could be allowed more options, including
At least alternative design, that's what we're talking about, I see.
Right. As long as we achieve performance requirement.
Yes.
So
I think that's another way, yeah. Achieve the performance requirement, then there are alternative design in a sense.
Right.
Yeah.
But the thing to remember is it's not static.
Yes.
So even if you designed it perfectly to start with, everything's going to change anyway. So performance is, it changes.
Because we're aging.
Aging, trees, trees growing, you can't get the soil parameters the same. They change with seasons, they change with time, everything's changing. So
That's okay. That's why
okay.
we got something to do.
Yeah.
I keep telling my students, sorry, any structural engineering here? Any structural engineering?
Structural.
No. I was my first job in Aero was structural engineer, graduate structural engineer. and then hire away myself in the toilet every day. Don't tell my, because so boring. Everything well established. You just BS8118, a serial code come out, design number, plug in computer, GSA, I still remember the software, and get the bending moment, shear force, and how many still in. First 2 weeks you're okay, but after 2 weeks you say, oh, what the hell am I doing? Okay. So I like challenges because that keep us alive in a sense. Now one thing actually, particular suction actually is very important. Has to, my view is has to be probabilistic based. Okay, and taking account of what's the probability to keep suction 10 kPa in a sense. 10 kPa is a lot when you're talking about federal safety. And also, as I said, like the railway lines, whether you like it or not, it's unsaturated. There's no argument. Okay? So it has to be considered. When you, I think grateful to GEO actually, I think it's a government policy, right? When there's a failure, slope failure, kill somebody in Hong Kong, has to do a forensic studies, correct? Yeah. It's a law requirement. That's why I involved a couple of those and doing the unsaturated soil testing, and then some analysis about. But of course, if nobody got killed, then probably no need. But this, you cannot make assumption a soil is fully saturated. Cannot. It can't be. When you do a triaxial test, you know you have to apply back pressure 200 kPa minimum in environmental and Hong Kong soil, and carbon dioxide first to get rid of air, and then back pressure 200. So it's no way you can saturate soil. I don't believe you can saturate soil in the field. Okay, think about Hong Kong soil. But unless you submerge the soil for years, then okay, of course. Okay. But anyway, so I think it seems to me probabilistic approach maybe as an alternative design.
Yeah, I think it's an alternative,
yeah.
And very also I think it's a scientific way of thinking about a problem. So it's a probability.
Yeah.
But it's not going to replace, I don't think, the classical approach. It's
not
going to be
easy.
in parallel.
Yeah, parallel. Yeah, that's what
I think.
Yeah.
And,
yeah.
I just wondered about suctions and slopes. Are constructed slopes do they ever include suctions as part of that? No, you have it in your back pocket as a sort of little bit of extra strength. It's not.
We do not count unsaturation effect in the design.
I think I had a line item in my which suggested that, but it'd be great if we could harness them and rely on them in some way.
Because in our experience, it's vanished quickly when it come when rains come in.
It goes away.
Unless we have perhaps hard surface or a impermeable protection on the surface, which there could be a different story.
Kind of seal them in somehow.
Right. Yeah. But nowadays there are many green groups around, and when we fix the slope, it's almost impossible for us to put hard surfacing on slopes nowadays.
Yeah, I think engineers are more comfortable with mechanical sort of stabilization, like roots or nails. I mean, those we're engineers. We like that sort of feeling.
That's what Michael tried to convince his funding agent to use roots as a reinforcement. But actually, the more significant effect is the roots suck out water, increase suction, and reduce permeability. That's more effective. If you do a quick sub calculation, it's much more effective than the mechanical means. But engineers, they like comfort. Because they're responsible to the entire society in a sense. They want to be sure, you know. Okay, are you there? The suction is there. Are you sure it's there? And so on and so forth. But if nowadays when you put the root vegetation on top, vegetation is going to help you anyway. You're going to suck out water, otherwise the vegetation cannot survive. Apart from some plants in Scotland or something, their leaves all gone away in a sense. But if the leaf go all away in some way, also means, am I right to say, means dry or no? In that part of the world, we are not familiar. No. A lot of water.
They go all soggy and slippery and land on.
Oh, a lot of water. Then you need some special plants.
That's the point strong. These fall off, and then and that's the.
And then the rain comes.
And that's the rain comes as well at the same time. So it's a double whammy.
Yeah, that's double whammy in this case. Yeah. So
further to Stephanie's saying about the network rail. They do not talk to each other. I mean, the maintenance team and the geotechnical team, right? That's why they
the drainage team.
Drainage team.
Yeah.
All right, I see. I can share some of our local experience here, because in GO, we actually hire a team of landscape architects. And we also produce our guidelines on landscaping. Actually, well, nowadays, as I say, there are many green groups around, and we see the need. And therefore, we proactively draw some guidelines to help our designer to select the species that can be grown on slopes, which also help the health of the slope, I would say. But in the slope design, we haven't taken into account those positive effects, for example, wood effects and things like that still. But because we as an engineer, we would think about, it may not, there could be uncertainty about, let's say, how deep the root would be and then how extensive they may grow. And therefore, this is this kind of hurdle that we didn't take this into account in the slope design. Yeah. But more research can clarify things.
Yeah, Julian raised a very good point. Is certainly we, I mean, geotechnical engineer, we have very limited knowledge about plants, I must admit. And we need interdisciplinary approach.
Right, true.
And even though I've been a farmer for 10 years, I still know very little about plants. And the more I know about plants, the more I know I don't know. Plants are very clever. Okay? That's why they can survive easily 100 years. Adaptation, they can adopt the environment very quickly, better than us. Okay? But the problem is we don't know them enough so that we can use them in a sense in the code. Unfortunately, I think there's something interdisciplinary.
But you mustn't forget these sort of, we talk about sort of interrelationship between various things. So, you know, having a planted slope might, it may not prevent it from failing, but it might mitigate the effects of that failing.
Yeah.
So, for example, you know, taking the case of a slope slide, you might find it stops material getting into a gully, which you then carry on down the gully, pick up more material, and of course issue down the bottom. So it's looking at the whole a systems approach, and the fact you may not stop it from failing, but it might well stop the mechanism of failure being such that it causes
or even minimize runout distance.
Yeah, exactly.
And so we did a sort of parallel test, and by putting sort of artificial plants with different root geometry, and then apply suction to the roots. And then 45-degree slope, as in the Hong Kong CDG, critical state in 39 degree roughly. No problem, no failure at all. Even though heavy rain, 1,000 year return period, nothing happens. And there was a viewer from Thailand. He was worried about saying no failure. How can I got my PhD? And exactly what you said. And then then I said, okay, don't worry. Include 60 degree, then you fail.
Over 70 degrees, you can't go into the. That's what we found in the UK.
Yeah. Well, you got 60 and then fail. But once you fail, then we can measure the runout distance. Exactly what is change the mechanism. And actually, different geometry, there's heart-shaped root actually prevent this or minimize. I would say minimize the failure's depth.
So it's not. So you may not be getting that absence ability, but it might well change the mechanism.
Exactly.
And then the flow on from that. Might change. So it's that sort of resilience helps resilience, even if it doesn't sort of mitigate total failure.
So to be fair to the oral speakers, CARe still cannot live alone, doing nothing there now. And I can see you are tired. I got a question for you.
Right.
So now you have, under your leadership, you built a nice facility, 28-meter long flume. How would that help mitigate or minimize influence of climate change?
We can use the soil model to study wetting and drying, cyclic initiation of landslides.
Okay, so you're thinking of initiation with
heating, perhaps on top, and rainfall systems, stuff like that.
So you collaborate with HKO here, I don't know whether. Okay. Thank you. Yeah.
So, well, I don't have any questions. Just Professor Anthony Charles in the break, and why you guys are sitting here like them and not interacting. So here comes with discussion to you all experts. Actually, I have a hypothesis, like the plants for the plant parameter and the processes that are involved in the plants and the soil. Just like the reinforcement of the roots and the suction, pull out, and everything. And there are plant processes like the stomatal conductance and everything. So they all are interrelated. So can there be a single theory that explains the entire thing?
We have expert here. Single theory.
Single theory that can explain the entire process as a whole. Just like in physics, they try to search.
Yeah.
I think as Charles said, it's a complex issue. You can these things act together in parallel. So but the point I was making earlier is that you cannot, and the point we all made is that you can't always rely on suction that comes from evapotranspiration, particularly when there's no leaves. But looking at the effect of that suction on consolidating the soil, that's something which is real. You can actually quantify, but that cycles, and then you go into sort of issues that you were talking about earlier. It's definitely about recycling soils over periods of years. Does that actually degrade the structure rather than actually make it stronger? So there's a lot of research still to be done, and that's why you're doing a lot of research in this area.
Yeah, so the detrimental effect of the trees.
Yeah.
Sorry, this doesn't really answer your question. This is just a follow on from what Mike just said. Because they suck water in the summer, they make the negative pore water pressures in the summer larger than they would be if they weren't there, but then they go away in the winter, so the positive pore water pressure is just the same as it would. So the cycle, the difference is bigger. So actually they might help with stability, but they may accelerate deterioration. So we need to explore that.
And that's something which you're looking at in your
but that's a particular problem when you've got deciduous trees and clay soils. So it's not applicable everywhere. That's the tricky thing with this. It's not, one rule doesn't apply to all plants and all soils. So we need to think carefully.
And also, since we're talking here about climate change, and I actually hinted at it when I was speaking yesterday, is that if you've got a plant which actually is working okay now, there's no guarantee that 20 years it'll be alive. And I think that's something which recent summers in the UK have actually got me thinking about. So it's not like sort of ramming a nail in your nose, and the nose it'll rust or degrade for a period of time. Yeah. And we've got this climate signal, which is changing the conditions, which might well invalidate your design later on because plants like that. So living organisms are complex, but as I always say at the end of every paper and every thesis, more research is required. But I'm optimistic that we can get there eventually. But you have to know what the limitations are.
You're optimistic.
Yeah. But you've got to know what the bounds are. Yeah. Again, anything. But
no matter what model you use, you must know the limitation first. I think that's number one. And I agree with Michael in the sense. At the end, we will do much better, but still there's quite a long way to go in a sense. Just so you know, the soil mechanics, as now that people call unified soil model. But you think about CARe model to start with clay, kaolin clay, lots of criticism, blah blah blah.
Granting gravel before that.
Yeah. So just take it sort of draw a parallel analogy. And I would say this is a new area in a sense at the beginning. Still a lot of things we don't know in a sense. You based on uncertain soil mechanics, how can you explain water from the ground level go up to 100 meter tall tree? No way, cavitation takes place. And even biologists, botanists, they won't be able to explain, but they postulate, but can't prove.
Yes.
Okay. You prove life, still, they have mechanical proof, but still it's mechanical proof, it's not so real proof in a sense. So a lot of knowledge we have to acquire before we can have a sort of more reasonable model. But good thing is we have bright young students here. Sunil sitting next to Professor Pervious, and this is our hope in the sense. Okay. You know, Sunday actually I didn't ask him to come, then he came to show up. So we need young bright people to champion. Okay. Of course, young IS junior fellow, as I told you, he did all the work, nothing to do with me in a sense. Okay. But you can kill me, don't kill him. Colopic. Yes, 2 questions.
Okay. I got a question to ask Professor Michael. So you mentioned that in the winter, the plant may die. So
the plant doesn't die; the leaves fall off. That's not the same. That's not the same thing. Yeah.
So, but we are here to talk about climate change. So, due to global warming, so the lowest temperature in the winter may increase nowadays. So, due to the global warming, will the winter less affect slope stability, which is protected by vegetation? So, or even will the global warming increase the slope stability of vegetated slope in the winter?
Yeah, I think it's in a way we're on the world. I think that if in the unlikely event of the UK becoming tropical, we would have a very different type of plant. So I think it depends. Native species in the UK have developed for native climate conditions, and so if it's a changing climate, you can't be certain that they will adapt quickly enough. Historically, when the climates have changed rather more gently, then I think plants have adapted much more rapidly, have adapted along with that. Whether they will adapt is a different question. So I think it's relying on them. But what you can always do is plant something else. But it takes many years to develop a full root system. And so, as I was saying very early on about maintenance, maintaining slopes. If you've got a plant slope and you're relying on those plants to do something, you have to maintain it, and you have to keep an eye on it. If you find that it is dying back, you have to sort of, one thing you can do, for example, if you've got a slope which you're relying on with plants and it's critical, you can come along and bash some nails in the ground, and do a hard solution rather than a bio solution. There's always that it's a last case thing you might want to do, but if it's a critical structure. But I doubt if you build something very critical and rely on the roots anyway. So it's a tricky thing. But basically, going back to your early point, is that the leaves in the autumn or fall, as you might call it in parts of the world, literally fall because the leaves fall off the trees, and the trees are still alive, but they're dormant, and come the summer, once the leaves start growing again in spring, they start sucking water and start that negative pore pressure all over again.
So you also mentioned the root can affect about 2 meter depth.
Yeah.
So, but we can say after almost 300 years growth, the willow goes. So the willow grow very high. So this means the root can go very.
No, they don't. No. That particular willow, they grow to about the maximum about 20. The black willow about 20 meters is the maximum height, and the roots go down, 2 meters max. I would say, typically. So they go out to quite a long way, but again, it depends on the soil type. There's this. The roots need to have water. They need to be able to penetrate the ground, and on a slope sometimes they follow gravity. They'll go along. Roots like everything else will follow the easiest route, literally. Well, actually, the easiest pathway to get to them. So they tend to grow laterally.
And the smaller roots actually also die back in the autumn. So the leaves fall off to protect the tree, and the smaller roots actually die back as well. So they don't keep growing. They die back, and only the larger roots remain in the winter.
Which I'm very clever. There's another question.
Yes, Dr. Michael. Which parameter index did you consider to determine amount of plastic root in your model? My means is about biomass or root area ratio, root volume ratio.
Yeah, I suppose in these studies they were fundamental studies. So we looked at our root area ratios were not dissimilar to the we did 2 lots of tests. We did some on the willows and some on tobacco roots, actually, for real roots. And so we took analogues which gave us similar root area ratios to those.
Okay, so thank you for participating in this workshop. We have learned a lot from each other. So could you join me to thank all the three all speakers? So we have gained sufficient information for the report next session. Thank you very much for your participation.